One, two, three, and okay. Morning, everybody. And as always, a huge honor to be here. And Lisbon happens to be one of my favorite places in the world, not because of the city, but because of the friends I have over here. It's, uh, it's a pretty amazing place to come to. Now, I do this talk every year, except maybe last year when I couldn't. And this is on neural networks, but this is not the standard neural network lecture that you would ever attend, because I'm not going to be talking about the how of neural networks. I'll not teach you or discuss backpropagation. I will not teach you the mechanics of neural networks. What I am going to focus on is what does a neural network do? Now, I'm not speaking of the mechanics of it. It can classify, it can model functions, but more at looking at the inside. So we try to get an idea of how these things operate. And so we learn about what a neural network is, historical perspectives, what it can model, and what they actually learn. But first, I must introduce myself. I've been using this picture for many years. Now it's no longer a joke. It's just stupid. But it's tradition. So that's me, right? I'm a professor. Okay. I also have affiliations to several other departments in CMU, including the machine learning department, music tech, and electrical and computer engineering. So we begin, without further ado, with what is a neural network? And even before that, why do I even bother to ask myself this question? Now, neural networks have become one of the major thrust areas in pretty much every pattern recognition, prediction, and analysis problem. When you speak of AI, you're not thinking of AI in the classical sense of the word, where we built expert systems and wrote rules or wrote little pattern classifiers. You're always thinking of neural networks right now. And that's because they're so good, they've basically established the state of the art in pretty much every field that they have been applied to. Now, where did it all begin? We've been working on neural networks since I was in college, early 90s, late 80s. And I have been poking around with this as well. And it was a very uninteresting topic because although the models were clearly capable, they never did anything useful for the longest time. And then suddenly, there was this explosion in 2016. All kinds of things happened. We've been working on speech recognition since the 1950s. Not me, of course, I wasn't around at that time, but still, the research community has been working on this topic since the 1950s. And in mid-2016, your Siri or your speech recognition-based device was basically, it was so unreliable, it was a party trick. And then suddenly in, I think, October or November 2016, Microsoft published this article where they showed that they had finally trained a speech recognition system that could outperform human beings on a fairly challenging task. How did they do that? They used neural networks. Or this one here. This was translation. Now, in October 2016, if you translated something from English to Spanish using Google Translate, and then translated the Spanish back to English, what went in and what came out would be so different that we used to use it for joking. We'd go to parties and say, ha ha, let's see what Google Translate does with this. And then suddenly one day that stopped happening. People were literally overnight, you had professional translators who began using Google Translate to provide the first cut of their translation. Why? They began using neural networks. Or this one here. We've been struggling with trying to understand and analyze and interpret images for decades. In 2016, this happened. You had a model that could find every object in a scene, find the bounding boxes, and tag every one of them by the class. Again, neural networks. Or games. Now, what is intelligence? We were not really clear, so we always thought about intelligence in terms of what we could do, and what is uniquely human and what could possibly not be put into rules. So initially, people thought this was chess, because chess is an intellectual game. There's no reason for us to evolve the ability to play chess. It has nothing to do with reality, right? And so chess was supposed to be the boundary of intelligence, but then in the 1990s, we came up with rule-based systems that could outperform the world's grandmasters. And after about 1996, no human grandmaster has been able to beat the best chess systems out there. So chess is out. But we still had Go. And the difference between Go and chess is that in chess, there are 10 raised to 120 possible game states. In Go, there are 10 raised to 180 possible game states. And so the hypothesis was that you need human intelligence and human intuition to actually be good at Go. And then 2016, this happens. The automatic system beat the world champion, and afterwards, no world champion has been able to beat an automatic system. Again, where did that come from? Neural networks, right? And so on. There was this landmark paper also in 2016. These days, if you feed an image to an AI system and it tells you everything that's in the image, you are not surprised. But in early 2016, this was not the case. If I fed any of these pictures to an AI system and asked it what was in there, it would probably stare at me like my dog stares at me when I give it commands, right? Have no idea whatsoever. And then suddenly there was this paper where the system could not only analyze the image, but give you text descriptions. It wasn't always right, but often it was close enough. And this happened once again because of neural networks and so on, right? These days, LLMs, they do everything. We are designing drugs, we are sequencing, we are finding the structure of molecules, we are generating music. This is from literally from yesterday by Taimur Hasib, who graduated. And both of these were done by AI. The first one is not by his system. The second one is a spooky shadow that's supposed to be scaring someone. By itself, yeah, it kind of looks scary. But then, and the fact that it's AI is astonishing given the detail and the level of information that you find in it. But then what makes it even more astonishing is that now you can feed this video, which was AI generated, to another AI. And it knows what's in the scene. Nobody told it what kind of music to produce. It has analyzed the scene. It has figured out that it's supposed to be spooky and that the kind of music that best goes with this scene is what you just heard. All done by AI, right? Again, what is behind it? It's a neural network. So, sorry. And so you have a variety of other problems: biochemistry, medicine, protein structure discovery, public health, driving, defense, speech processing. Right now I'm reviewing a paper that one of my students wrote on predicting on performing high frequency trading using neural networks, defensive high frequency trading. And these things outperform anything that a human being or previous systems could ever come up with. All of these again with neural networks, right? So, of course, there's this bottom line. Things have gotten to a point where if you even want to think of finding a job in the tech sector, you better be familiar with the subject. Otherwise, you're going to starve to death. It's not a guarantee that you'll find a job. There's a lot of competition. But not knowing about neural networks is a guarantee that you won't find a job. Now, so what's this? What's this magical neural network that does all of these crazy things? From where we stand, it's just a box. It's a black box. Something goes in, something comes out. A voice signal goes in, transcriptions come out. A game state goes in, a prediction for the next game state comes out, and so on, right? But what's in the box? That's the key bit. And for that, we have to go back and think of what these tasks are. Now, all of these tasks, whether it be playing games, captioning images, predicting the stock market, these are fundamentally human tasks. You're not going to find dogs, lions, cats, or any other species doing these things, right? So to understand how these could be done, perhaps we have to begin by the root of all human intelligence, the human brain. But what's in the human brain? We don't know. So even before the human brain, maybe we should think of what the brain does. And people have been worrying about this. What does the brain do exactly? And how does it do it? They have been worrying about this for over 2,000 years. The oldest recorded history of scientific inquiry into how the human brain operates goes back to 400 BC, Plato, where he wondered about what makes it tick. Here are all the things a human being can do. A human can learn, they can solve problems, you can recognize patterns, you can create. But the craziest thing, you can just be having a shower. I'm sure all of you have had this experience. You're in the shower stall, having a shower. You have absolutely no input other than the water falling on your head. And then you have thoughts, and you have creative thoughts, and you come up with solutions to problems you didn't even know you had. Why do we do this, right? And how? So this is something we'd like our systems to emulate. Question is, again, how does the brain work? And Marvin Minsky said it best: if the brain was simple enough to be understood, we who are being powered by this brain are going to be too simple to understand it. It's fundamentally some kind of an uncertainty principle where the sheer complexity of it that makes us operate as we do also ensures that you can never understand it fully, right? But that doesn't stop us from trying. And so the oldest model of people who tried goes back to Plato, who's right in the middle of this painting. Ever since I went to Rome, I'm not able to enjoy this painting because I found that who's that person to the left of Plato? Is that Socrates? Is that Plato? Aristotle, right? Aristotle's shin is too short, and that bothers me a whole lot. The fact that this has survived for 500 years and nobody pointed this out bothers me even more. But anyway, this is the famous school of Athens painting, and showing all the scholars as they were known in about 1500 AD, painted by Raphael. But the person in the middle, he's the first person to actually begin worrying about recorded person. I'm sure people thought about it earlier as well, to begin worrying about how the brain works. And the idea he came up with is associationism. Now, associationism is something that we still use today. So this is a theory that has survived 2,500 years. It's still very much active, and it's a part of every machine learning task you ever performed. And the basic idea is this, that we associate inputs with outputs. In other words, it's a function. So every time you see lightning, a little later, in your experience, you hear thunder. So after a few such experiences, later, if you hear thunder, you're going to think lightning must have struck nearby. Or if you observe lightning, you're going to say, okay, let me wait for the thunder. Depending on the distance of the lightning, I'm going to hear it sooner or later. Now, you form this association, and it's on the basis of these associations, which are built from your own personal experience, that you make your inferences about the world. And that's how even your neural networks work. You have given them input-output pairs. What it really learns is associations between the input and the output. But the question again, when you're studying the human brain, is where are these associations stored? And by the mid-1800s, we had kind of figured this out. So by the way, I have a rule in my class. I'd expect all of you to follow it. Can you shut your laptops? Every last one of you, that lady there. Mind shutting your laptop? Please. You there, can you shut the laptop? Yes. All of you, right? I'm taking time out of my schedule to come here and give you a lecture. The least you can do is to respect my time and keep your laptop shut. Even if I bore you to death, you sleep in the chair, but keep your laptop shut, okay? All right, so let's continue. So by the mid-1800s, we know this. We know what the brain is constructed of. The brain is constructed of lots and lots of neurons which are connected to each other. It's a network. So how the brain operates has to be something that's encoded in the structure. But then what is the structure? How does it actually operate? That theory came in the mid-1800s itself. People realized with the development of microscopy that the brain is this huge connection of individual units, neurons, where each neuron connects out to many neurons, and each neuron is connected into by many neurons. So clearly, there's something about the structure, and the first person to come up with a model for how information is stored in the structure was this guy, Alex Bain, in 1873. So modern neural networks have their history traced back 153 years to 1873. And not only his idea was that the information is stored in the connections. And he not only said the information is stored in the connections, he came up with models for it. So here is one of his examples. Here is a network with 3 inputs and 3 outputs. And depending on which of the inputs is high, different output patterns occur. So the idea that different input combinations could result in different outputs for the same circuit, this is something very obvious to us. In 1873, this was anathema. And so he got scorned, he got laughed at, but he came up with this model. He also came up with something even more profound, where he showed that depending on the duration and the intensity of the input, the output could change. The same circuit, all that changed was the duration and the intensity of the input. And so here, for example, if you have a short input, then only X will fire because it gets 2 inputs. But if you have a long input, Y will fire because it gets 3 inputs, right? Things like this. And so here is how he also said the whole thing could somehow learn. It said when two impressions concur or closely succeed one another, the nerve currents find some bridge or place of continuity, better or worse, according to the abundance of nerve matter available for the transition. So he came up with a theory for how these models actually learned, right? So, miss there? You mind shutting the laptop? I asked everybody to shut their laptops. Please do this, right? Okay. So uh, the problem was this. He was really sure about what was going on initially, but then he began doubting himself because people doubted him and they eventually convinced him he was wrong. In 1873, he figured that you need 1 million acquisitions of concepts for your brain to function. But then by and by, he realized that those 1 million acquisitions are fully formed acquisitions. What about the partially formed ones? And eventually came to the theory that idea that, we just don't have enough brain for all of this to happen. So he apologized, he withdrew his claims. And when he died, he was a broken man because he thought he had made a mistake. But which is unfortunate because the truth is, he was right. Our brain is enormous. We have 80 billion neurons in the brain. Those 80 billion neurons have 100 trillion connections. So there's more than enough brain matter for you to store everything that you will ever experience in your life and more because of the sheer size of these models of what's in your head. And so here is where we are. The human brain is this machine which is composed of lots and lots of connected units where the individual units are very simple. And all the information is in the connections. It's what is called a connectionist machine. Neurons connect to other neurons, and the processing capacity of the brain is a function of these connections. And so when we speak of modern neural networks, these are connectionist machines. They emulate this structure. So this is what a connectionist machine is. It's a network of processing elements. All world knowledge is stored in the connections between the elements. Now, how is this architecture different from the architecture of the processor in your phone or your laptop? Can someone tell me? What's the standard architecture in your standard processor? Anybody? I'm sure you know the answer. So the answer is this. Your processor is what's called the von Neumann architecture. It has a processing unit. It has a memory. And to make the processor perform some new operation, you don't have to change the processor. You only change what's in memory. And then suddenly it's doing new operations. It's performing new tasks on new data. On the other hand, if you have a machine where all the program is stored in the connections, then every time you want to change the program, you're going to have to build entirely new hardware. And so that's the challenge with connectionist machines. Connectionist machines are not good in terms of structural efficiency. And which is why when we build connectionist machines, you don't go off and actually build hardware. You're going to use your von Neumann architecture to emulate it. Still, you see the fundamental difference between the two, right? And so here's where we are. Neural network-based AI has taken over most AI tasks. Neural networks originally began as computational models of the brain, or more generally as models of cognition. The earliest model of cognition was associationism. The more recent model is connectionist, where neurons connect to neurons and the workings of the brain are encoded in these connections. And so current neural network models follow this architecture. We are emulating the brain, and these neural networks are connectionist machines. So here's what it looks like. You have a network of processing elements. The individual elements, we have not said anything about it, but they're simple. And all the information is in the connections between these elements. But then we have to go back and ask, what's in those individual elements, right? To ask that, if you're emulating the brain, let's go right back and look at the brain again. And the individual elements in the brain are the neurons. Now, what does a neuron look like? Typically, it looks like this. You have this head called the soma, which has a lot of locations for incoming connections. when the combined input exceeds some threshold at a rough level of approximation, this head generates a signal which goes down this long leg called the axon and goes out to other neurons. And here's a fact that all of you must be aware of, that neurons in your body do not actually replicate, right? They do not undergo cell division. And there's a reason for this. If all the information is in the connections, there's no way a neuron can replicate and retain the connections. That neuron becomes functionally useless. And so for that reason, your brain, your body has all the neurons it's ever going to have. They're developed during childhood. Once you're 3 years old, you're not going to be developing a whole lot of new neurons because of this property. Those neurons cannot divide. If you want new neurons, you need stem cells, neural stem cells, which don't give you quite as much regeneration as you would like. And another thing that is funny about it is that that long axon is protected by a little bit of fat. It's called the myelin sheath. And so what scientists have found is that how intelligent you are doesn't depend on how many neurons you have in your head. It depends on how much fat you have in your head. The more fat you have, the more protected your neurons are, and the smarter you are, right? So if somebody tells you you're a fathead, that's the biggest compliment you can get in your life. Now, so fine, here are the units. How do you model them? We waited for a long time, even after knowing all of that, until we came to these guys. Warren McCullough, who was a professor in the University of Chicago at that time, and Walter Pitts, who was a homeless guy who turned up at McCullough's door asking for work. He wanted to work on math. Obviously, from this picture, McCullough is the guy on the right, and the hobo is the guy on the left, right? So, and Walter Pitts was 20 years old when this happened. And he came up with the first mathematical model for neurons. And this famous paper, A Logical Calculus of the Ideas Immanent in Nervous Activity, Bulletin of Mathematical Biophysics. I've read this paper 3 or 4 times, and I must confess that I have never managed to get past the math on page 1 because I didn't understand it. But Pitts managed to produce it at age 20. And here's what they actually modeled it as. They modeled this, it was a literalist model of the neuron, where they said the neuron has 2 kinds of incoming connections: excitatory synapses, through which signals come in, and inhibitory synapses, which are connections where when anything happens, when there's any activity over here, it freezes the neuron and prevents it from producing any output at all. And then they showed how this little model can compose all kinds of Boolean operations. So in each of these examples, the neuron fires if it gets at least 2 inputs, unless one of those inputs is an inhibitory input. So the figure to the top left, the incoming neuron 1 connects to neuron 2 through 2 connections, which means every time neuron 1 fires, neuron 2 is going to fire a little bit later. So it's just a delay. In the figure to the right, both inputs 1 and 2 are connected to neuron 3 through 2 connections each, which means regardless of which of those fires, the neuron is going to get 2 inputs. So that's 1 or 2. The one to the bottom left, what is that? Can anybody tell me in this case? Anyone? I know you guys are sleepy. It's 9 in the morning, but it's all 9 in the morning for me. Yeah. You said something? That's an ant, right? Because both 1 and 2 have to fire. And so this is more interesting. It is 1 and not 2. Because if 2 fires, then that's an inhibitory connection, and the neuron will not fire. So you can compose all kinds of, once you realize you can compose Boolean gates, you realize you can compose any Boolean circuit with these units. The problem was these guys overclaimed. They said given enough of these, you can model a Turing machine, which is true, but they didn't provide a learning mechanism, and much of the work was incomplete. We were waiting for a learning mechanism, and that waited for this guy, Donald Hebb, who, like the scientists of those days, was also crazy. He was a hobo, he was a farmer, then, I don't know, he became a teacher, then he decided he wanted to become a neurophysicist, so he went to Harvard, so easy. And then he produced this landmark work on how neural networks learn. And his theory, stated very succinctly, was neurons that fire together, wire together. How does it work? Here's how neural connections work. When one neuron connects to another, it doesn't actually touch. Neuron 1 has a big head, and it's very close to the second neuron synapse. And anytime a signal travels through neuron 1, chemicals come out of this head and they excite neuron number 2. So the strength of this connection depends on the size of the head. And what they found, what Hebb found and what he tried to mathematicalize was that anytime a neuron fires and it causes the second neuron to fire, the head gets bigger, which means the strength of the connection becomes larger. And so if you wrote it in math, you can say the weight of the connection between one neuron and the other increases every time the signal X in the neuron causes the signal Y in the neuron that it's connected to also become high. So if both X and Y are 1, assuming everything is Boolean, then the weight increases. It's a very nice idea. It's a very simple formula. It's still the basis of many learning algorithms in machine learning. It has a problem. And the problem is this, that the weights can only increase. They can never decrease. So eventually, for any finite capacity of network, all the weights are going to saturate. This network is not going to learn anything. It's a very nice idea, but it needs some corrections. And for that, we had to wait for this guy, Frank Rosenblatt, who was a psychologist, logician in Yale. And he invented the basic units of what you now know as neural networks in 1958. In 1962, he went out to celebrate his 42nd birthday, went rowing, and he drowned and he died. So, which is a bit of a tragedy. But in that short time, he managed to actually shake the world. So what was his idea? He modeled the neuron like so, very similar to what McCullough and Pitts did. He said that every neuron has a collection of inputs, and every input has associated with it a weight, much in the same way that Hebb said that every connection had a weight. And so the neuron sees a weighted sum of inputs. And if the weighted sum of inputs exceeds some threshold, the neuron fires and produces a 1. Otherwise, the output is 0. Now, this is not his actual model. His actual model was more complex. He was trying to model the eye. And so his actual model had many layers of these kinds of units, where you had signals going out, signals coming back, all kinds of crazy stuff happening. And what he showed was that something of this kind can compute pretty much everything, which is true. And the funders of the day, the Navy and the Army and such like, they got very excited. And here were some news reports that came out. The embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. This was the claim in 1958. Frankenstein monster designed by the Navy that thinks, 1958. 1960 happened, and it was not walking, talking, or reproducing itself. Now, this was very disappointing to the Navy, so they stopped funding this research. And we had to wait for another 20 years before things could take off. Mostly because of too much expectation. But the key point was the basic unit was this guy. And a second tragedy happened. The second tragedy that happened was that when Frank Rosenblatt said this model is capable of anything, he was right. Within limits. We'll see that later in this lecture. But people began associating those capacities with this smaller unit, which is just one component of his model. And that exaggerated belief led to other kinds of problems. Now, Rosenblatt also came up with a learning rule where he showed that if you want to learn the connections between two neurons, you can use this very simple example, that the weight keeps getting adjusted by the product of the input and a second term. Now, this looks a lot like what Donald Hebb said, that anytime one neuron fires and it causes the other neuron to fire, the weight increases. So it's the product of the two. Here, instead of having the product of the input and what the second neuron produced, so Hebb's rule is basically unsupervised. Rosenblatt's genius was to introduce the notion of supervision. If somebody asks you, what did Rosenblatt bring to the table that Donald Hebb didn't, or McCullough and Pitts didn't, it's supervision. That there's the notion of a target. There's a D that each neuron is supposed to produce. And what you're actually going to increment the weight by depends on how wrong the neuron is, depends on the error. If the neuron is correct, you don't have to change the weight. If the neuron is making a mistake, then you adjust the weight in proportion to the error. And so The neuron, again, it's the same thing. If you have every incoming connection has a weight. So I've represented the neuron like so. The circle represents the body of the neuron. You have the incoming edges. The number on top of the edges represents the weight. And then you have the inputs. The total input is compared to the threshold. If it matches or exceeds the threshold, the neuron fires. Otherwise, it doesn't. All variables are Boolean. And so you can see the figure to the top left. Once again, if x and y are both 1, the total input is 2. The neuron will fire. But if either x or y is 0, the input is insufficient, the neuron will not fire. That is going to be an AND, right? Bottom, the threshold is just 1. So what would this guy be, the one at the bottom? Anybody? That's going to be an OR, right? Very simple. And what about the third figure? What is that? Anyone? Yeah. That's a NOT, right? Because you have a negative 1 as the weight. And so you can see how these things can model stuff. And it turns out that this unit is very powerful. One of these units can replace an exponentially sized conventional Boolean circuit for many problems. That's amazing if you think about it. But in spite of that, this unit cannot model an XOR. There's no combination of weights where the output is going to be X XORed with Y. And so Rosenblatt knew this. It turns out that in order to bypass this, you need something more complex. A single unit by itself, although it's very powerful, is not powerful enough. So what can we do? We go back to the brain. Now, the brain is not a single neuron. The brain is a network of neurons. So if you want to emulate the neuron, the brain, it's not enough to have just one of these units. You need a network. You need networked elements. And so once you begin networking them, here's what you get. Now I have 3 of these units. And I have 2 units in the middle, which I'm calling the hidden layer, simply because I'm not interested in their individual outputs. Not that it's hidden in any way. It's just that it's not interesting. What's interesting is the final output at neuron, from the neuron at the tip of the arrow, right? But the neuron on top is computing X or Y. The neuron at the bottom is computing not X or not Y. And the output neuron is ANDing the 2. And now suddenly, by connecting 3 of these neurons, I can compute the XOR. So the lesson here is that once you begin connecting these guys in a network, you can compute pretty much any Boolean function, like this crazy Boolean function of 4 variables here, just by figuring out what the neurons must be and what their weights must be. So here's where we are, right? We said that neural networks began as computational models of the brain. They are connectionist machines. They comprise networks of neural units. The first model was the McCullough-Pitts model, which was the first model to actually model neurons as Boolean machines. And they hypothesized that the brain is performing propositional logic, which was a huge breakthrough. It doesn't seem so remarkable now, but back in the time, it was phenomenal, right? But they provided no learning rule. Hebb came up with a learning rule, neurons that fire together, wire together, but this is unstable, as we saw. And then Rosenblatt came up with a variant of McCullough-Pitts neuron with a provably convergent learning rule, which was a variant of Hebb's learning rule. And what Rosenblatt brought to the table was the notion of supervision, that there's a target output for every neuron, and every neuron is going to be trying to achieve this target output. And once you have those neurons, you can connect them up into networks, into what we call multi-layer perceptrons. More on that in a bit. And they can compute pretty much any complex Boolean function. But then our brain is not Boolean, right? I'm not working off Boolean inputs and Boolean outputs. You guys are not pixels, which can take the value 1 or 0. Everything is continuous. So given this, how does the brain work? How do I operate on non-Boolean inputs? And how do I produce non-Boolean or non-Boolean outputs? So the same model still works. How so? Here's my neuron again. It has a bunch of inputs. It computes a weighted sum of all of these inputs and then compares this weighted sum to a threshold. I can split it into 2 operations. The first operation is computing the weighted sum of all the inputs. The second operation is putting this weighted sum, this affine term, through a threshold function. Once I separate it in this manner, I can even replace that threshold with other functions like a sigmoid, which looks like the threshold function, like a smooth version of the threshold function. And now in the structure, the inputs x1 through xn are real valued. So they're not Boolean anymore. Associated with all of these inputs are weights, which are also real valued. And the output can be real valued. It can be viewed as a probability in some settings, right? But for the sake of explaining what's going on inside, I'm going to continue assuming that everything is Boolean, the outputs at least. And so here's our network. A single neuron, not even a network, just a single neuron, right? It gets a series of inputs, collection of real valued inputs. Associated with each input is a weight. It computes a weighted sum of these guys and compares this weighted sum to a threshold. Anytime the input is greater than the threshold, it outputs a 1. Anytime it's less, it outputs a 0. So the boundary is where this weighted sum is exactly equal to the threshold. And when I say summation wi xi equals b, that is the equation of a hyperplane, right? So the boundary is a line or is linear. And so this is what the function looks like. It's a Heaviside function. There's a hyperplane. On one side, the output is always 0. On the other side, the output is always 1. And if you're wondering on which side the output is 1, it is the side in which the set of weights, which you can think of as a vector, points. In that direction, the output is a 1. In the other direction, the output is 0. So once you know how this operates, you can see why this can model all kinds of Boolean functions. There's a line. On one side, the output is 1. The other side, the output is 0. Now, if the inputs are Boolean, if I have two inputs, the only four allowed combinations are 0, 0, 0, 1, 1, 0, and 1, 1. If I draw the boundary, like I show in the top left, then for the upper three, 1, 0, 0, 1, and 1, 1, the output is 1. For the other one, the output is 0. What function is that? Which Boolean function is that? Anybody? That's an OR, right? Now, if I want to convert the OR to an AND, all I have to do is to move the line so that only 1, 1 is on the one side. And now I get an AND, right? If I want to make it a negation, I rotate it. Everything below is 1, everything above is 0. So this depends only on one variable. So you can see how this simple perceptron can also operates on Boolean variables. And you can also see why this cannot model an XOR. I'll leave you to think about it for a bit. I'll ask you again in a while, okay? But once I have this, that what a perceptron is doing is basically computing a function which has a boundary, a linear boundary, and the output is 1 on the other side, one side, and 0 on the other side. I can compose crazier things, like a network which produces a 1 when the input is inside this pentagon and 0 outside. And I'm sure you already know how this would work. What I can do is have one neuron which outputs a 1 above this horizontal line and 0 below it. A second neuron which outputs a 1 to the left of this line and 0 to the right. A third one like this one, 1 below the line, 0 above, right? A fourth one like that one, 1 to the right of the line, 0 to the left. A fifth like this. And now, which is the only portion of the space where all 5 neurons output a 1? Anyone? Inside the pentagon, right? So all I need to do is to sum their outputs and compare the output to a threshold 5. And amazingly enough, the sum is 5 only inside the pentagon. It's something other than 5 everywhere outside. I've constructed a little network which computes a pentagon decision boundary. Well, how does that help? Here's what I can do now. I can do something crazier. I want a network which produces a 1 inside either of the two pentagons and a 0 outside. I have one subnet which produces a 1 inside the first pentagon, another one which produces a 1 in the second pentagon. I OR the two, and suddenly I have a decision boundary that's a double pentagon, right? But once I do this, I can do crazier things. I can compose all of these decision boundaries, something that fires if the input is inside the man-shaped outline and 0 outside. How would I do that? I can just sort of decompose these things into unions of little polygons, and voila, I get an arbitrarily crazy decision boundary, right? And so when I perform classification, if I give you a digit, like in the MNIST corpus, it's a 764 pixel input. I'm asking you, is this the digit 2 or not? In that 764 dimensional space, there's a region of the space within which all the 2's reside, and that region has a boundary, maybe something like this peanut shape, right? And all we need to do is to construct a network which outputs a 1 inside this boundary and 0 outside. And using this little trick, we know how we can do this, right? So what this means is that MLPs, these multi-layer perceptrons, which are connectionist computational models, we saw they can model Boolean functions, but the new lesson is that they are Boolean machines. They can represent Boolean functions over linear boundaries. They can capture arbitrary decision boundaries. It doesn't matter how complex the decision boundary is. I can compose a neural network that captures it to arbitrary precision. And if you haven't ever understood how that happens, I just explained how, right? So, but what does this thing actually learn, right? I'm talking about perceptrons. What's the perceptron really learning? Let's look at the individual perceptron again. Is there a semantic to it? Now, a perceptron operates like so. It computes a weighted sum of the inputs, and still using the threshold activation. If the weighted sum exceeds a threshold, it outputs a 1. If it's less than that threshold, it outputs a 0, right? What is this weighted sum? If I look at this term, this way x summation xi wi, I can put all the weights in a vector w, all the inputs in a vector x. And what I'm really saying is I'm computing the inner product between the weights and the input. If this inner product exceeds a threshold, I'm going to output a 1. Otherwise, I'm going to output a 0, right? What is an inner product? Now, something that almost all of you probably know, even though you haven't thought about this too hard, in high dimensional spaces, all vectors are the same length. It's very easy to prove. If you look at the ratio of the surface of a hypersphere to the volume of the hypersphere, as the dimensionality increases, this ratio tends to 1. And so when you're in 1,000-dimensional spaces, pretty much every vector lies within epsilon of the surface of the hypersphere. There's almost nothing inside, which means that in high dimensions, all vectors are approximately the same length, number one. Number two, when I compute the inner product between two vectors, this is length 1 times length 2 times cos theta, right? So when I say the inner product is greater than a threshold, I'm just saying the angle between the two vectors is less than a threshold. And so what this comparing the inner product to a threshold is really doing is that it's saying if the angle between my input and the weights vector is less than some pre-specified threshold, then that neuron is going to fire, otherwise it won't fire. So the weights of the neuron, they are a template. They are telling you what you're looking for. And you're comparing the input to these weights in terms of the angle with respect to these weights. And if the angle is small enough, the neuron fires, otherwise it doesn't. So this is like a correlation, right? So now if I were to work on this LED grid, and my task is to build a little network that determines if this what is being displayed in the grid is the digit 2 or not, I don't have to do any training. I can literally just draw the number 2 in the grid and set my weights to be this, this pattern that I have drawn in the grid. And then every input that comes in is you're going to be computing the inner product, which is the correlation. So if you got an input like the one in the second figure, this inner product is too small, it's probably not a 2. If you got something like the one on the right, the inner product is 0.8, probably a 2, right? So I don't even need to sit around and learn this stuff. If I know what the neuron is doing, I know it's looking for patterns, I can handcraft the patterns and the neurons, right? And so if I'm learning a bigger task, like looking at these ancient watches which had LED displays, sometimes they'd go back and you get bad and you get crazy pictures on it. If my job is to figure out if this thing is actually, whatever is on it is actually a digit, what I would need is the first layer neurons, which capture all the key structural components of digits, horizontal lines, vertical lines. I don't have to train the network. I can literally just handcraft these neurons to look for these patterns. And then the second level neurons are going to be looking at these guys and saying, do these things combine to form digit 0? Do they combine to form digit 1? And then a final OR. So once you understand what these neurons are doing, you realize that for trivial problems, you can actually handcraft these networks because the semantics are very clear, right? Of course, you typically learn this stuff, right? The second layer is going to be looking for specific digits, and then you combine the lot. And so MLPs we saw are the new lessons are MLPs are Boolean formulae or over patterns detected by perceptrons. Perceptrons are looking for specific features. And so in classification, the network fires if the combination of the detected basic features matches an acceptable pattern for the desired class of signal, where an acceptable pattern is an appropriate combination of features. If you're doing face recognition, I could literally design this thing to look for noses, lips, or whatnot, right? So any questions? Anything? No. But then we're looking at classification. We're looking at Boolean functions. What else can a network do? It can perform regression, right? It can compute real valued outputs. How can you modify the same thing to compute a real valued output? We'll spend a little more time on this. But just roughly speaking, think of this network which has a scalar input. It's producing a scalar output. It has two perceptrons. The one on top fires, meaning it outputs a 1 if the input exceeds threshold T1. The one at the bottom fires if the input exceeds threshold T2. If I sum the outputs of these two neurons with weight -1 and 1 respectively, what happens is that the overall network outputs a 1 if the input lies between T1 and T2 and a 0 otherwise. So you end up with an output which looks like the figure to the right. And once I know how to compose that, I can compose crazy things like this function over here. All I have to do is approximate this function as a sequence of pulses, right? And for each one of these, I just need two neurons, which produces a 1 in the right range and 0 elsewhere. Then I can scale all of these guys and sum them up. And so this network over here is approximating the blue curve. And I can make this approximation arbitrarily precise. I can make this simply by increasing the number of substructures. And so you give me a limit to how much error you're willing to tolerate. I can compose a network for you that will approximate the function at less than that error. And so the lesson we end up with over here is that MLPs can also model continuous valued functions, which is pretty amazing. And so what we've learned in all of this is that MLPs can model pretty much anything. They can model any Boolean function. They can model any classification boundary. They can model any continuous valued function. Not every MLP can model all of these. What we are really saying is that if you give me a function, a Boolean function, or a classification boundary, or a real valued function, I can construct an MLP that computes it to arbitrary precision using exactly the mechanisms that we just saw, right? So, questions? Okay, guys, I know you guys are sleepy, so I'm going to do something. It's morning for me as well. So the next time I ask you, I'm going to ask you to raise your hand if you understood. Okay, and you're going to have to. You don't have a choice. That includes all the guys in the back. I have the ability to, because of this magical clicker, I have the ability to walk to the back of the room and I will bully you, all right? So let's continue. So here we are, the recap. What is a perceptron? It's computing a weighted sum of inputs. It's comparing it to a threshold, right? And it fires if the weighted sum of inputs exceeds the threshold, or alternately stated, I can think of the threshold as a bias term. It fires if the weighted sum of inputs plus bias is positive and 0 otherwise. And of course, once I write it in this manner, then I can replace the threshold function with a soft function like a logistic. And something that goes from 0 to 1 very smoothly. And that's just like a softer version of the threshold. Now, have you guys been taking the machine learning lectures? Yes, no? Okay. What is this? Have you encountered the logistic function? Yes or no? Can you say that aloud? Thank you, right? What else could you replace the logistic function with? Is that the only function you've learned? Or is there anything else that looks very similar but could compute a probability? I'm sorry, I didn't. Can you say that aloud? No, that's not a probability, right? I want something that looks like this. Anything else? Hyperbolic tangent goes from -1 to 1. Yeah, but if you smooth it, if you shift it and normalize it, it becomes a logistic. So that's not an answer. Anything else? Yeah. So here's what you guys are not being taught. No, nobody tells you this stuff. The logistic function is basically based on the logistic distribution. It's just one of an entire class of functions. I could base it on the Gaussian. The CDF of a Gaussian looks just like this. And when you have the CDF of a Gaussian, that's called a probit rather than a logit. And then you have other such things. You can choose your density function, and the CDF is always going to look like this. And depending on the function that you choose, you get slightly different behaviors. The reason we work with the logistic is that it's so convenient mathematically. Okay? Yeah. Again, it's still going to be a softmax. It's just that, if you take the cumulative density function of any density, it's going to have the same shape. It just won't be as mathematically clean simply because they have ugly formulae, right? But anyways, getting back here, if I'm not interested in something that goes from 0 to 1, I can replace it by other functions like a hyperbolic tangent or a ReLU or a soft plus, right? And other things. And what is the multi-layer perceptron? You basically have a network of these guys. But in this, there's a magical term, layer. What's a layer? Does anybody know what a layer is over here? Yes?
After that you break like linearity with some activation function. So like composite functions, the same layers that you showed with
There's a very formal definition for layer. How many of you are familiar with that? Right? Not many. Let's go through this. You guys, again, the whole point of this lecture is try to demystify some of the magical terms that you use. So somebody could ask, and you go to an interview and you don't embarrass yourself and the rest of us, right? This is generally layered. What is a layer? It's a deep network. What's a deep network? Anybody? Anyone? What's a deep network?
Something with multiple layers.
How many?
Right.
How many? More than
More than
two?
Yeah.
Yeah, but then what's a layer? Okay, let's answer these questions, right? It starts with graphs. Almost everybody here is familiar with graphs. It starts in a directed graph, a directed acyclic graph. That's the kind of graph you're speaking of. All the edges are directed. And such graphs provably have a source or sources from which you have only outgoing arrows, and sinks in which you only have incoming arrows. If you didn't have these two, the graph cannot be directed and acyclic, right? And so the depth of a graph is defined as the longest path, the length of the longest path from a source to a sink. So the figure to the left, the depth is 2, although there's a path of length 1 from source to sink. The figure to the right, I have paths of lengths 1, 2, and 3, but the depth is 3. And so a neural network is just a graph. You have the input is the collection of all sources. You have the outputs are all sinks. And now, if you look at all of the neurons in the network, the neurons in the network have a depth with respect to the input. There's something special about all of the red neurons in my figure. What is that? Anyone? Yeah. The depth, they're all depth 1. Those are layer 1. It doesn't matter how I drew it, right? All the neurons in green, they are depth 2. The longest path to these neurons from the input is length 2. So that's the second layer. The yellow neurons are depth 3, and the blue neurons are depth 4. That clear? Right. And so when you think of a neural network of this kind, this guy has the actual depth of the network itself is the depth of the output layer with respect to the input. Again, the implicit assumption is that every neuron in the output layer is the same depth as every other neuron. This doesn't need to be true. In that case, things get a little more complex. We don't live on those complexities. We work with simple stuff. And so that network to the left, the depth is 3. The network to the top, each box represents a layer. The depth is 2, although there's a path of just length 1, right? The network in the middle, With the cat, that is a depth of 4. You get the idea, right? It's the length of the longest path from the input to the output. And what is deep? If the depth is greater than 2, which means you need more than one hidden layer. If you have more than one hidden layer, it's a deep network, otherwise it's a shallow network. That's terminology, okay? And the MLPs, we saw the inputs can be real or Boolean. The outputs can be real or Boolean. You can have multiple outputs because you can have multiple neurons in the output layer. And what can this network compute? What kinds of input-output relationships can it capture? We've already seen this, right? We saw that MLPs can compose Boolean functions. They can compose real-valued functions. But there's got to be some limit. If I give you a network of some size, can it compute everything? Clearly not. So what is the limitation? Let's start with Boolean functions. How well do MLPs model Boolean functions? Now, we've already seen that a single perceptron can capture any Boolean operation, right? Once again, what was the one to the top left? Just to see if you were awake. And the bottom left, and the bottom? Okay, thank you, right? And this could not compute an XOR, right? But it can do all kinds of other things. Here is this network, this single perceptron. This perceptron is going to output a 1 if all the first L inputs are 1 and all the remaining outputs are 0. Any other pattern is going to make it output as 0. Why is that the case? So look at this. If all of the first L inputs are 1 and all the remaining are 0, then the total input going into the circle is L. If you flip any one of these, because the lower ones have weight -1, the sum is going to decrease. If any of the lower ones become a 1, the sum decreases. Any of the upper ones becomes a 0, the sum decreases. So there's a very specific combination. The first L are 1, the rest are 0. That's when it fires. Here's the reverse, right? This fires if any of the first L are 1 or if any of the remaining are 0. So again, how do I compute this? I look for the one condition where it will not fire. And that is where all of the top L are 0 and all the bottom L are 1. And then I just reverse the sign of the threshold and it works. So I won't get into the details, but you'll be able to figure it out. It's fairly straightforward. And so you can see how this is it's a fairly complex unit. But then it's even more impressive than that. This neuron will fire if there are at least k inputs that are 1. Now, if you want to do this thing this is a majority gate or a generalized majority gate. If you want to do this with a standard Boolean function, you're going to have to test for every possible combination of input. A Boolean network, which computes majority, is exponentially sized in the input. I can do that with a single unit using a perceptron, which is why perceptrons are so much more powerful than simple Boolean gates. And which is why for the longest time, people kind of overestimated its capacity, right? And of course, once you begin modeling these guys, it gets even more interesting. But even regardless of all of that, it can't capture an XOR as we saw. And the reason for that we saw was that an XOR actually has 2 boundaries. An XOR outputs a 1 for 0, 1 and 1, 0, and zeros on either side for 0, 0 and 1, 1. So you want a function which goes up and then comes down, whereas the perceptron only captures 1 boundary. And so anything that cannot be captured by a single boundary cannot be modeled by a single perceptron. You need networks. And we saw how the XOR can be modeled by a network of 3 neurons, right? And so we also saw once we do that, we can compose all kinds of really crazy Boolean functions. And the Boolean functions that you compose using perceptrons are going to be much smaller than what you would build if you actually did them using Boolean gates. And so there was an entire industry of research on what is called threshold logic in the 60s, 70s, and 80s, which were trying to exploit this. Now it's sort of built into your processors. But then, if you look at the number of gates, the layers in the network to the left, I have 2 hidden layers. It's a very simple function. You'd expect that as my function becomes more complex, the number of layers keeps increasing, right? So if I give you an arbitrary function and I ask you to give me a network, multi-layer perceptron that computes this Boolean function, how many layers will this require? Can anybody take a guess of this? How many layers will a network need if I gave you an arbitrary Boolean function? Yes. 2? Okay. Thank you, right? So the answer is very simple. I can model this as a CNF or a DNF. And so what is a Boolean function? A Boolean function is a truth table. You have a collection of input combinations, and you have an output, which can be 1 or 0, right? And if I have n inputs, how many different Boolean functions can I compose? Anybody? For n inputs, how many Boolean functions can I compose? Anyone? You guys have all, like, there are 100 people in this room. I'm sure one of you knows the answer. 2 to the 2 to the power n. Can somebody do better than that? 2 to the n plus 1. Can someone do better than that? Guys, 100 of you. This has to be better, right? You can't just be sleeping. So how many rows will that table have? Anyone? N inputs. How many rows will the table have? That's for 5 inputs. If I have n inputs, how many would it have? 2 raised to n. Each one of those can have an output of either 1 or 0. How many functions can I compose? 2 raised to 2 raised to n, right? Because I have 2 raised to n rows. Each of them can be 1 or 0. So it's a the capacity of this truth table is enormous. But then at the end of the day, a Boolean function is just a truth table, and I only need to store the guys where the output is 1. And once I do this, I can write a DNF formula, which is a sum of products. So that first clause over there, this guy, it says that the output is 1. It's not x1, not x2, x3, x4, and not x5, which is the first row in the table. Not x1 means x1 is 0, right? So it says the output is 1 if x1 is 0, x2 is 0, x3 is 1, x4 is 1, and x5 is 0. The second clause says the second row, x1 is 0, x2 is 1, x3 is 0, x4 and x5 are both 1. So it's not x1, x2, not x3, x4, and x5. I have one clause for each of these rows of the table. And we know that a perceptron is a universal AND, so I can build a perceptron for each one of these clauses. And then I can OR the lot. And so since every truth table on the planet can be, every Boolean function on the planet can be expressed as a truth table, I can actually compose a neural network, a multi-layer perceptron with one hidden layer that computes it, which means that one hidden layer networks are universal Boolean functions, right? But then there's a catch. How large will that hidden layer get? Anyone? So let's look at the answer. And for that, I'm going to give you, how many of you are familiar with Carnot maps? One person. Okay, 2 people. 2% of the room. Good. Okay. So a Carnot map is a topological way of representing inputs. Now here, this is a function of 4 inputs, W, X, Y, and Z. The rows represent every combination of W and X. The columns represent every combination of Y and Z. What's special is that if I look at 2 adjacent rows, they differ in only 1 bit. So the top row and the bottom row connect. So also every column differs from its neighboring columns by 1 bit. So the rightmost and the leftmost columns connect. So this whole thing is actually a toroid, like a donut, right? And every one of those squares represents one of the clauses, one combination of these input bits. And the highlighted ones are the ones for which the output is 0. And so this one has 7 outputs. So if I wrote a simple DNF formula, it's going to have 7 clauses. That's not a great idea. 7 is too many. I can reduce it. Why? I can begin grouping things together. If you look at the first column tells me that the output is 1 regardless of what W and X are. So I can group those 4 guys and say the output is 1 whenever YZ is 0, 0, right? And so each one of these groups, which just groups up neighboring cells, gives me 1 clause, and the final function only has 3 clauses. It doesn't have 7. And so I can make these things smaller. And this is a standard problem in designing Boolean functions. You start with your truth table, and then you come up with ways of compressing it in this manner till you get with the smallest representation. And that's what you're actually going to capture with your circuit, right? And so this one needs 3 neurons in the hidden layer. But then if I'm looking for worst cases, what is the worst case where I cannot reduce the function in any manner over here? A checkerboard, because there's no grouping, right? If I do a checkerboard, if I have n inputs, how many cells do I have that cannot be grouped for n inputs? 2 raised to n over 2, right? Half of them, because I have 2 raised to n cells. And so this cannot be reduced, right? This is with two. So if I want a DNF formula, if I want to do this with a single hidden layer, this one is going to need 16 neurons, 8 neurons in the hidden layer. This is only 4 inputs. If I have 6 inputs, and I'm going to represent them topologically very similar to Carnot maps, there are 64 combinations, but your one hidden layer network needs 32 neurons in the first layer. Can you think of any way of making this smaller? Anyone? Anybody? Adding more layers, but how does that help? You have to look at the math. What is this function, right? So in general, if I'm careless, I will require 2 raised to n minus 1 neurons in the hidden layer. But then if I actually look at the function, which is exponential in n, these are XORs. What is an XOR? An XOR is a function that flips every time I change one bit. That's all it is, right? An XOR is a checkerboard. So that first one is W XOR X, XOR Y, XOR Z. The one to the right is U XOR V XOR all the way to the end. And I know that an XOR can be modeled using only 3 neurons in 2 layers, right? Which means that this first guy has 3 XORs. So I need 3 times 3, 9 neurons. The second guy has 5 XORs, which means I need 5 times 3, which is 15 neurons. In general, the number of neurons I will require is simply going to be 3 times n minus 1. So here is the case. If I was doing this naively using a shallow network, I required 2 raised to n neurons in the hidden layer. If I allow myself to be deep, then I only need 3 times n. Actually, I need 2 times n. So the difference in size is enormous. You go from exponential to linear in the number of inputs. There's a catch. Can somebody notice the catch over here? I know you're falling asleep, so I'm challenging you. Can you notice the catch? Anybody? Again, we're talking of what a neural network can model and what the limitations are. The depth of this network depends on the number of inputs. If I just say my network has only 6 layers, I cannot arbitrarily increase the size of the network. Why so, right? If I have, let's see how I can rearrange this network. If I have n inputs, if I allow myself to go deep, then I can make the network linear in n and still have only 2 times log 2 of n layers. And that's by using this associative property of XORs. So I can XOR them pairwise. So the first 2 are XORed, the second 2 are XORed, and so on. The outputs of these of the XORs of these pairs can once again be XORed in pairs, and I can keep doing this. So after every 2 layers, the number of variables is halved. So I get 2 times log 2 of n layers, right? What happens if I go below this? If I go below this and I say I go below 2 times x2 of log 2 n layers, now I have a bunch of new variables which must be XORed, but I have only one hidden layer left. And at that point, now the number of neurons ends up being exponential in size. If I don't have an exponential number of neurons, I'm not going to model my function properly. Now the XOR is a nasty function. If I get 1 bit wrong in an XOR, the error rate is 50% for a binary function. So if I miss 1 neuron over here, that network is useless. And so here, if I have less than that exponential number of neurons over there, I cannot compute the function to any degree of usefulness. It's going to be a rubbish network, right? And so deep Boolean MLPs that scale linearly with the number of inputs can become exponentially large if I recast them with fewer than the minimum required number of layers in the network. That makes sense to everybody? Right? And this works for any odd function. I can take any function that I'm trying to learn. Eventually, I'm going to end up with something that looks like an XOR. And at that point, I'm going to need the number of additional layers is going to be dependent on the logarithm of the variables I've left remaining. And if I use fewer than those layers, then I better make my network wide, or I'm not computing the function at all. So now the XOR is really a parity problem. Any Boolean circuit of depth D using AND, or NOT gates with unbounded fan-in must have size 2 raised to n raised to 1 over D. So this is something called, so the point is, the catch I mentioned is that the depth of the network depends on the width of the input, the number of neurons in the input. Now, people who work on theory like to categorize these things into categories. So the AC0 class of circuits is the class of circuits of fixed depth. And the AC0 class of functions is the class of functions that can be modeled using fixed depth regardless of the number of inputs. It turns out that parity and most functions do not belong to the AC0 class, which means you really do need depth, variable depth, right? And there's more theory to it. Shannon, of course, invented everything on the planet. Between Shannon and Turing, they left us with nothing. So Shannon actually has a theorem which says that for n greater than 2, there's a Boolean function of n variables that will always require 2 raised to n over n gates. And his logic is very simple. Like I said, if I have n inputs, there are 2 raised to n possible functions. So if I randomly choose one of these functions, it's going to be with probability approaching 1 of the nasty functions that you cannot model with a neural network. So with a finite size neural network. So it turns out that the set of Boolean functions that a finite size neural network can model is almost 0 in size. For n inputs, the total number of possible functions is 2 raised to n. Of these, the set that you can model is order 2 raised to n, which when you take the ratios is basically 0. So we like to believe, that we like to work in the belief that everything can be modeled with a neural network. The theory says otherwise. What the theory is telling us is that we are incredibly lucky in the functions that we choose, right? So an MLP is a universal Boolean function. It can represent a given function if it's sufficiently wide, sufficiently deep. Depth can be traded off for exponential growth of the width. Optimal width and depth depend on the number of variables and the complexity of the Boolean function, right? Questions? Any questions? No? Okay, can everybody say yes together? Thank you. You're supposed to say no. I asked you if you had questions. Anyway, so MLPs are universal Boolean function machines. Even a network with a single hidden layer is a universal Boolean machine. That's what we saw. But then deeper networks may require far fewer neurons than shallower networks to express the same function. It can be exponentially smaller. We're going to see a few more fun examples of this. What is the time? So this goes on to 10:30, right? Okay, we have 15 minutes. Great. So let's go back to MLPs as classifiers. Here, the MLP is a function over real inputs. And it's a function that finds a complex decision boundary over the space of reals. That's what a classifier is. So how does this work? Again, we saw that a single perceptron basically computes a Heaviside function. It can be a smoothed version of a Heaviside function if you use a non-threshold activation. And so this is a linear classifier, right? Basically, if I look at only a single perceptron, it's saying, here's this boundary. On every side, on one side, I'm going to say everything is 1. On the other side, I say everything is a 0. And so when you want to perform classification with it, you really are trying to find you're assuming that everything can be, the good and the bad can be separated by a hyperplane. And the problem is that of finding the hyperplane. But then we saw that we can compose more complex things with these Heaviside functions, like this pentagon, right? Here, the network must fire if the input is in the colored area. The way we did it was we had 1 neuron for each of the lines, and then we combined them, right? And then if you want a more complex decision boundary, I have 1 subnet for the first pentagon, one for the second pentagon, then I group them together, I OR them together, I have the double pentagon. And then I can use the same logic to compose more complex boundaries like this guy, where all I would do is to shatter my ugly pattern into many small polytopes. I can have one subnet for each of these polytopes, and then I can combine them all over again to compute my crazy boundary. Now, before I proceed, right, I'm going to go back to this business of depth. Can I compose? You see how this thing is being shattered. Clearly, I need to be able to shatter it in a manner where every single subunit can be composed using a subnetwork and they can be ORed, right? So how many hidden layers will I need to compose an arbitrary decision boundary of this kind? Anyone? How many hidden layers would I need? 2 hidden layers? So suppose I told you I can do this with only 1 hidden layer. Can you think of how I would do this? Not even for this complex one. Let me try the simple double pentagon. How are you going to do this for just 1 hidden layer? My claim is that it's possible, yes. Break it down by? Exactly. Right, anybody else? Let's actually hold on to that thought. That's partially right. Anybody else? Okay, let's go back to you, right? That's a smart answer. How do you break it down by pixel? Yes, but this is an n-dimensional space, right? And so once you begin doing that, things sort of break down, right? So, but that's basically what we do. And the rule for that is based on the pentagon, right? Actually, let me take it back. Let me take it to the diamond. If I want to compose this diamond decision boundary, what am I going to do? I have one line, one neuron for each of the 4 sides, and then I'm looking at the sum of the outputs. The sum is 4 inside, and outside it's less than 4. If I use a threshold of 4, I am going to get a diamond, right? If I look at the sum, the plot of the sum is like the figure to the top right, right? It's 4 inside the diamond. It's not 4 outside. Now, what would the decision boundary look like if I used a threshold of 3 over here? What's it going to look like? It's going to look like a hash, like a cross, right? So now the real problem is that the cross has this area of sum 3, which is infinite. It's going out to infinity in every direction. That 3 guy is a problem, because if I try to approximate a function using 2 diamonds, the 2 3s would intersect. And so I'd have 2 regions which are target areas where the sum is 4, and where the 2 3s intersect, the sum ends up being 6, which gives you this undesired region, which you end up including in your decision boundary. So what we really want is the sum to be 4 inside the diamond and 0 outside. Can I do that? Increase the threshold? No, this is the sum. This is what the sum is, right? And so here is what happens. Suppose I try to build a pentagon. Now the sum is 5 inside. Outside it's less than 5. But unlike in the case of the diamond, if you look at the area where the sum is 4, it's no longer infinite, it's finite, right? So the figure of the sum is shown to the top right. You can see it's 5 inside, and then 4 for some star-shaped region, and then later it's 3, right? If I go from a pentagon to a hexagon, that's what the sum looks like. It's 6 inside. The area where it's 5 is even smaller, and then the area the sum keeps reducing. Does this give you any ideas? What's the obvious next step? Take the limit, right? If I go from 6 to 7, you can see that the region where the sum is 6 is even smaller. If I go from 7 to, say, 16, these are badly plotted. This is MATLAB barfing. But you see what it looks like, right? And what do you think the limit is going to look like? The sum is going to look this. was with 1,000 sides. This is, I keep increasing the number. That's what it looks like, right? That was actually done for me by one of my undergraduate students who came to me after class, and he wrote the math down while I was doing the lecture. So I began using it in the next class. And that's the crazy function. It's actually the cylinder. It's perfectly n. N is the number of sides inside, and then it falls off rapidly, falls off exponentially as you go outside. And so a good approximation to that is something that looks like this. The sum is exactly n inside the cylinder and n over 2 outside the cylinder. If I actually add an extra term which subtracts the n over 2, then it becomes n over 2 inside the cylinder and 0 outside the cylinder. And now I have this network where I have a whole bunch of neurons, but n has to be very, very, very large for this to work. And then when I sum their outputs, the sum is exactly n over 2 inside the cylinder and 0 outside. I can take two such sub-networks, right? And where one of them composes a cylinder here, the other composes a cylinder here, and then I can sum their outputs. And because the sum is 0 outside the respective cylinders, they don't interact. So the sum of the outputs of these two subnetworks ends up being a double cylinder. Now I can slice it, and I can get two non-intersecting circles as my decision boundary. Now we can see how we can get even crazier boundaries, right? Using just one hidden layer. The cost we pay, the number of neurons, n, is very large. And so if I want to approximate this double pentagon, the way I would do it is like so. I'm going to fill it up with circles. I'm going to have one subnet for each one of these circles. This is not exact, but I can make the error arbitrarily small by making those circles as small as I want and packing them as tight as I want. And so in the limit, you give me a continuous function, a decision boundary. I can compose a network with just one hidden layer that will approximate it to arbitrary precision. You give me the error, I will go below it, right? So a one hidden layer MLP can model, that's a hidden layer, any classification boundary. MLPs, one hidden layer MLPs are universal classifiers. Right? So what's the lesson over here? The figure to the left and the figure to the right are getting the same decision boundary, more or less. The figure to the left has 12 hidden neurons. The figure to the right has essentially infinite, right? So what did depth get us? Why is depth important? The moment you go deep, the size of the network that you're going to need to model the same function is going to fall not just exponentially, but super exponentially. It's going to fall rapidly, right? That's why depth is essential. So we've looked at optimal depth in generic nets. We've looked at worst case decision boundaries for threshold activation functions, generalizes to other networks, right? So I'm just extending this example. I'm not going to be talking about this topic after the break. So we're almost at the break. Let's say I want this decision boundary. I want ones in the golden regions and zeros in the gray regions. Now this is a crosshash. It looks like an XOR, right? But if I just want to do this with one hidden layer, if I do this naively, I'm going to end up with essentially needing infinite neurons. If I do this with two layers, I need 56 hidden neurons. Why 56? Because this pattern is composed of 16 lines. So I need 16 neurons in the first layer. And then there are 40 golden boxes. So I need 40 neurons in the second layer, and then I need the OR. So the total number of neurons required, hidden neurons required, is 56. Easy, right? 57 total neurons, including the output. But then the topic I want to mention is that of capacity, right? Can I make any of these layers thinner by just adding more depth? That's the question here, because we keep talking about depth versus width trade-offs. So what is the trade-off? If I make a network D narrow, can I compensate by making it deep? Now, let's get the answer to that question here. The neural network can represent any function provided it has sufficient capacity. It has to be sufficiently broad and deep to represent the function. Not all architectures can represent every function. How? let's take this thing, the same pattern. I'm using threshold neurons, right? Again, burn this in your head. I am speaking of threshold neurons. We will go past it in a few minutes. If I have only 8 neurons in the first layer, the 8 neurons with threshold activation are just going to tell you on which side of 8 random lines I am, right? So it's going to give you information of some kind. If I have only 8 neurons in my first layer, can I compensate for it by having, say, 7,000 neurons in my second layer or 7,000 additional layers and still get this checkerboard? Do you think I can? I'm using threshold activations. Is the answer yes? Anybody? Okay, you say no. Why not? You've lost information. This is all the information that you will have after the first layer, right? There isn't enough information over here to now compose the rest of the checkerboard. All you're saying is, am I to the left or the right of 8 lines? Even if my first 8 lines look like this, the only information I have is which of these squares I'm in. I have no information about the position within these squares, right? And so if the number of neurons in the first layer goes below 16, there's nothing I can do to recover. There is a minimal width I need in each layer. If you go below that minimal width, you could be dead, right? That making sense to everybody? Right? And so, but then there's a way of getting around it. Same thing, right? Even if I have 16 neurons in the first layer to capture all 16 lines, if my second layer doesn't have 40 neurons, I can't capture 40 boxes. If I have only 39, I'm missing a box, and then there's nothing I can do downstream by adding more layers that can recover the rest of the pattern, right? So not all architectures can represent any function. But then, is there some kind of an escape clause? A network with less than 16 neurons in the first layer cannot represent this pattern exactly. But then when I began explaining this, I said I'm using threshold activations, right? So how does that interact with this? What the threshold activation does is only tells you on which side of a boundary you lie. So if I have 4 neurons in my first layer, once I go past the first layer, the only information I have is in which of those 5 bands I am. I don't have any further information. So it tells me for each boundary, on which side of the boundary I am, and there isn't enough information for me to reconstruct the rest of the pattern. How can I fix this? Anybody? Different function for the threshold. What kind of function? What is required? A threshold is nonlinear. A threshold is about as nonlinear as you can get. Something that preserves information about the distance from the boundary, right? And so if I use something like this, it's not merely going to tell me which side of the boundary I'm on. It's going to tell you how far I am from the boundary. If I have that information, again, keep in mind that it's necessary but not sufficient, because I could still, if my boundaries are still parallel, there's no way I'm going to be able to construct the rest of the boundaries which are orthogonal to it, but I can keep adding more boundaries parallel to the existing boundaries. And so if I have something like a sigmoid, then it's going to tell me how far away I am from the boundary. So when I go past that layer, I still have enough information to compose additional boundaries and additional characteristics for the function. And so that matters, right? The gradation provides information to subsequent layers to capture information missed by the lower layers, which means the activations you want should be the kind that actually have maximum gradation between these two guys. This is more important, useful than that one. Why? Why is this guy more important, useful than this one? Anyone? Actually, this has to do with the distance. When I'm out here, it doesn't distinguish between this guy and this guy, right? Whereas here, it continues to give me distinctions the farther away I go. And so the kind of activation functions you want are the kinds that retain information about the distance from the boundary for as far as possible. So ReLUs, leaky ReLUs, soft pluses, all of these are useful activations. Threshold activations are no good. Sigmoids, they are useful within a very small region. TANH, useful within a very small region. You get the idea, right? And so narrow layers can still pass information to subsequent layers if the activation function is sufficiently graded, but requires greater depth to permit later layers to capture patterns. And even so, you're dependent on luck in the sense that if I use only 4 neurons in the first layer and they all capture parallel lines, there's nothing I can learn orthogonal to these boundaries because that information is still lost, right? I think we're out of time. I'll stop right here and we'll pick up after the break. Yeah.
Just a fast announcement. So we'll have the poster sessions now. Have today, tomorrow, and the other 2 days. So feel free to use the placards in the lobby, in the coffee break area, and you can have the posters there during the day. The next day we'll have other posters. Thank you.
Welcome back. We are starting the second session 10 minutes late. I'll give you a few minutes to settle down. The same rules apply to the second half as they did to the first half, which means I expect all your laptops to be shut, your phones to be off. And whenever I ask you, you're going to shout out yes. So I'll wait a few seconds for all of you to settle down, and then we'll begin. Okay, everybody ready? I need a loud yes. Okay, thank you. So that means your laptops are shut. Guys, those of you looking at your phones, please turn them upside down. Keep them upside down. Standard requirements in my room. I say the same thing regardless of whether I'm speaking to undergraduates or Nobel laureates. So you must know this, right? These are the rules that apply. Okay. And so if I find somebody coming and staring at your phone, I'm going to come to you personally, to your chair, and ask you to turn the phone off. It can be very embarrassing. So don't do this. All right, here's where we left off, right? We said MLPs are universal Boolean functions. They're universal classifiers. They're universal function approximators. We saw even, I keep saying single layer, that's an error. A single hidden layer MLP can approximate anything to arbitrary precision, but could be exponentially or even infinitely deep in its width, which is a problem. We saw deeper MLPs can achieve the same precision with far fewer neurons, so they are more expressive, although it comes with some caveats. So we'll spend a little more time on this before we go off and try to see a little more about what networks actually learn. So the neural network can approximate any function, but if I want the network to approximate a function, I must know what function it is I'm approximating, which means that the function itself needs to be known a priori, right? So more generally, if I want to approximate a function, I'm given some function g of x, and I'm told, compose a network to compute this function. And so if this is given, then I can actually learn the network to compute this function. So I can learn a neural network, for instance, to compute sine of x or exp of x. Or you give me a crazy function, and I can learn the network to compute it. How would I do that? I'm going to assume that the network has sufficient capacity. We've already discussed this notion of capacity. It needs to have sufficient depth in all its layers. It needs to have sufficient number of layers. You need to have the right kind of activation. All of these I'm going to assume are given, right? So then the network itself is completely characterized by the weights and the biases, the network parameters. Even with the right architecture, If I set the network parameters to be something, it's going to compute some function, not necessarily the function that you want it to compute. So for example, if the function I'm trying to learn or I'm trying to model with the network is the function g of x. For any current setting of w, the network computes something else, which is the f of x that I've shown. So you want to model the dashed blue curve. The function with the current set of weights gives you the red curve. There's a gap between the two, shown by the shaded area. So if I want to optimize the network to compute this function, what would I do? I'm going to try to modify the weights to minimize the shaded area. I want it to go to 0, right? So to do this, I need two things. First, I need a way of quantifying this shaded area. What is the shaded area, right? There's got to be a mathematical formula, and the formula has to be optimizable. So I will first define a divergence function. I'm just calling it error, but the divergence function has this characteristic that anytime the two terms are not the same, it's going to be positive. If they're the same, it's going to be 0. And then in some intuitive sense, so there's a bit of a chicken and egg, right? I can say if the error is large, the divergence is large, but that's a non-statement because the divergence is the error. So your notion of what is an error is a lot more intuitive than that. It's abstract. So from a mathematical perspective, it's just a function, which is 0 when the two are the same and positive when they're not. But from an intuitive perspective, or maybe you can characterize it differently, as the gap increases, the divergence function must increase. So that's what our error function is. And that shaded area has to be defined in terms of this divergence function, which is the integral of this function over the entire space. And we are going to learn the parameters of the network, the W, to minimize the shaded area. The problem is that you need the entire dotted curve. You need all of g of x. In reality, you're not going to get g of x. No one is going to come and say, here is this function, model it. Because if I had the function, why would I need the network? I don't need the network, right? So what you will have in reality is that you're going to get a few snapshots of the function. This is what you call collecting training data. Here is the input, here is the output. Here's another input, here's another output. So you have snapshots. And from this collection of snapshots, somehow you have to learn the entire function. And so that's basically what we have. Going back to the original figure, you're going to have a bunch of training instances shown x1 through xn. You can compute the error at each of these training instances. And we are going to approximate the shaded area as the average of the lengths of the lines at all these training points. And the hope is that if you minimize that average, then somehow the shaded area will also go down, right? Of course, that need not happen. So our aim is to find the network parameters that fit the training points exactly, assuming the network architecture is sufficient, and assuming that at any input there's a unique output D. This can be violated under some conditions. And hopefully the function that we learn that matches the training data at all the red dots is also correct everywhere else. The problem, of course, with this is that you can learn something completely crazy. So the way we would do it again, you're going to define the error between the actual network output, f of x, and the desired output, y. And this is a function of the network parameters. You're going to sum this error over all the training points, or average it over all the training points. You are learning network parameters to minimize this average, and hopefully you learn the correct function. But then nothing stops you from learning this guy here, right? Because all you've got is the value of the function at those dots. And so now you have to begin making some kinds of approximations and assumptions in the hope that these assumptions will somehow make the network, the function that you've learned, the network, fit the true function over a wider range of areas. This is the generalization problem. Now, one of the simplest things you can assume, which we assume a whole lot of, is that if at any given x, the desired output is y, then at a small distance from x, x plus epsilon, the output y is also going to be with some y plus delta. A small perturbation of X results in a small perturbation of Y. Now, there are different ways of imposing this constraint, but this is the only tool we have left in our disposal. That if I have this value here, if I move the value around, the output must not change a lot. So how can you impose this? You can impose this in a variety of ways, but since we are speaking of architectures, one of the ways to do this is to impose it through architectures. Again, to give you an idea of how badly underspecified we are, I like to give this example. Let's say you have a 100-dimensional input. 100 dimensions is nothing. Your typical MNIST picture is 764 images, right? Pixels, right? Your typical data is millions of dimensions. So 100 is tiny. And furthermore, let me assume that each of these components is binary. It takes only two values, 0 or 1. That means the total number of points that I can have in my space is 2 raised to 100, which is about 10 raised to 30. So I have to learn the function over 10 raised to 30 points to learn the function fully. If I give you 10 raised to 15 training instances, which is 1,000 trillion training instances for this tiny, tiny, tiny problem, right? You know what fraction of the space it covers? It covers 1 in 10 raised to 15, basically 0. It doesn't matter how much data you give me, you're giving me no data at all. And you're asking me to learn the function from this 0 data. To give you a better idea of how bad this is, if I scale it down logarithmically to a single dimension, it's the equivalent of this. I give you 1 point and say, okay, learn me the function. This is basically the problem that we are dealing with every single time you're learning a machine learning problem. You're tackling a machine learning problem, particularly with deep neural networks, right? Which are a lot more unstructured than, say, a linear model where you say, I'm going to draw a line. So how can we deal with this? There are many different mechanisms that we have proposed in the literature. All of them have to do with the fact that if I perturb X a little bit, Y should be perturbed only a little bit. But then in this example, there's no notion of perturbing X. X is binary, right? And so what can we do? There are things you can do through the architecture. And for this, we're going to take advantage of the fact that for a given number of parameters, deeper networks impose more smoothness than shallow ones. Why? Because when I have a deep network, the first layer learns some function. So it learns some wiggly function in the space. Then anytime I'm assuming, of course, that the layers are not completely unbounded, that the weights and such like are not allowed to blow up and go to infinity. They're bounded. So in this case, anytime you have one layer operating on the output of the earlier layers, it keeps smoothing the function. As you go deeper down, the function gets increasingly smooth. And so for a given number of parameters, if you say, I'm allowing you 1,000 neurons, how do I redistribute them in depth versus width? It turns out that deeper networks improve more shallowness constraints than shallow ones. And this is something that you can use to your benefit. So I'm going to show this through a couple of examples. I had to give credit where it's due. The guys who did these examples for me are both now professors at MIT, but this was done a long time ago, 8 years ago. So we're trying to learn these two decision boundaries in this example. In one case, the decision boundary is shaped like an arrow. I want a 1 inside the arrow, 0 outside. In the other case, I want this double square. I want a 1 in the inner square and a 1 in the outer square and 0 elsewhere. We've sampled 1,000 training points from both. And then these two guys, who, as I told you again, are professors at MIT, so they're not dumb. They threw every trick they had at their disposal at this problem. These are the best decision boundaries they got out of these 1,000 training points. Anybody see a similarity out here? Unless there was something in the coffee you drank in the break, you're not going to see any similarity, right? So what can we do about it? Let's go ahead and look at the width versus depth trade-off. Similar examples. In one case, I'm trying to model a bear, a decision boundary that looks like a bear. The other one looks like this nut, the bolt. And in each case, we had 660 neurons. That was our budget. So the 4 examples shown in the first, I'm modeling them using 4 layers of 115 neurons, 3 layers of 220 neurons, 4 layers of 165 neurons, 6 layers of 110 neurons, and 11 layers of 60 neurons. So broad versus deep, right? And you can see how the decision boundary changes. It's the same number of neurons in each case. As the network is redistributed to make it deep rather than broad, it begins to learn the boundary better and better. It does this for the function to the left. It also does this for the function to the right. So there are 2 ways of doing it. One is I can actually make my model architecture biased towards depth because that tends to learn functions much more cleanly. It comes at a cost. As the network gets deeper, it's harder to train, but when you do train it, it gives you better results. And the other one, of course, is that you can just take, instead of 1,000 samples, you can take 10,000 samples. It tends to work across the board. So having more training data, these are the 2 things that you always have at your disposal. An order of magnitude more training data and better architectures, where deeper architectures are always better than shallow ones. And for any amount of training data, simply because it doesn't matter how much training data you give me, you're giving me 0 data, the bias must be towards the deeper networks. So I'm done with the architectures. I stopped a little early because we needed the coffee break, but any questions? Yeah.
Give you recent information. You said that there's a limit to how wide a single layer
So
has
that's
to be.
not the boundary that didn't give me distance information. That was the activation function that didn't
Yes.
give me just
Yes. So
distance.
in the, like, if you use sigmoid or something more informative, do you still have a limit, or can you have like single neuron layers that you can still
So
scale to?
the number of neurons you need has to be at least as many as the number of dimensions in your data. That's a minimum requirement, because otherwise you're always going to lose information, because just having one losing dimensions means you lose information regardless of what you store. So even if your activation is just an identity function, which retains everything, if you lose one dimension, that thing is gone. Right.
I'm not sure if I missed it, but initially you mentioned that even in the Boolean constraint, there are some functions which cannot be learned by neural networks. Like what we learn is a subset. It's just that we are very lucky at the functions that we have to learn.
So I'm not saying that it cannot be learned. I'm saying that the size of the network that can be required to learn it is exponential, or almost exponential in the size of the input. And so if for any n variable input, there are 2 raised to 2 raised to n possible Boolean functions. Of these, the number of functions that can be modeled reasonably using a finite size network is basically 0% of the entire set. It just so happens that we manage to fall into that 0% more often than not.
Is there any intuition or like any, I don't know, vague understanding of what the other set is and why it happens that the most of the functions that we try to model with our like daily tasks with neural networks fall in that which can be modeled? Like,
I don't have the answer for that, because I've spent most of my life investigating the 0% and not the ones that I can't model, right? But I'm sure there's some characteristic to it, because there's randomness over there, right? The worst case example that I came up with, which is the XOR, is really not the worst case. It's in fact one of the friendliest functions you can think of with threshold activations. So that set is huge, but for obvious reasons, me and people like myself, we haven't spent a lot of time investigating it. But yes, I'm sure there's something to be learned from it.
thank you.
Any other questions? Okay, let me continue, right? So what does the network learn? We are trying, again, you're given a collection of input-output pairs. We are trying to learn the function, right? Now, let's say I'm trying to learn to classify. So I have these red dots and blue dots. They are 2 different classes. I'm trying to build a classifier, which means I want the network to compute the function shown to the right. It's a 1 inside the double pentagon and 0 outside. That function is going to classify this data perfectly, except that nobody gave me the function, right? They just gave me the training data, the red and the blue dots, so I have to learn it all from the red and the blue dots. So furthermore, in real life, the red and blue dots are not going to be so cleanly separated. They're going to find some blue dots on the red side, some red dots on the blue side. So how do you go ahead and learn these functions from these data? Let's start with the simplest example, a linear decision boundary, right? Here the boundary is a hyperplane. And so you're trying to learn a single perceptron because a single perceptron learns a linear boundary, which is a 0 on one side, a 1 on the other side. So it's a Heaviside function. And you're trying to learn this only from the data that you're given. The red and the blue dots, you don't actually have the boundary. And so from just these guys, you have to learn the boundary, which means you're going to have to learn the weights and the bias of this perceptron from just these dots. So how can one go about this? I'm going to get rid of the bias simply because it's an extra term which causes more annoyance than anything. And so a simple way of getting rid of the bias is to say I'm going to add an extra input whose value is always equal to 1, and then the corresponding weight becomes the bias, right? So I've handled the bias. And now the actual classification function becomes this. I'm considering the weighted sum of inputs, and the output is 1 whenever the weighted sum is positive, 0 otherwise. I have to learn these weights so that the red and the blue dots, my training data, are cleanly separated. Again, I'm assuming just a two-class problem. I'm assuming that the data can be separated by a hyperplane. My job is to find what this hyperplane is. So this is the problem. You're given these two classes of data. I want to find the hyperplane such that it cleanly separates the two classes. Now, in doing this, I'm going to use a very famous old rule which was proposed originally by Rosenblatt. And for that, I want to point out something first. How do you characterize a hyperplane? I can draw a vector which is at 90 degrees to the hyperplane. So the hyperplane now is the set of all data that are orthogonal to this vector, which is what I will call the weight vector. So there's a vector W, and the hyperplane is the set of all points that are at 90 degrees to W. So I can now state this in math, saying W transpose X equals 0. The inner product between X and W is 0. That's what it means for the data to be at 90 degrees to the vector. And the hyperplane is the set of all X's that satisfies this value, right? And then what happens to data on either side? For things that are, for vectors which are not on the hyperplane, but they're on the same side as W, W transpose X is going to be positive. Everything that's on the other side, W transpose X is going to be negative, right? So if I have a single positive training instance, I just say, here's this red dot, the class is +1. What is the best weight vector for the hyperplane that classifies this training point perfectly? The obvious weight vector is the one that points directly at the data itself, because that's when the plane is at a maximum distance from the data point. If I rotate the plane, the vector even a little bit, the plane will rotate, and it's going to get closer to the data point on one side or the other. It's going to be at the maximum distance from the data point when the weight vector points exactly at this data point, right? Similarly, if I have a negative instance like the blue dot, then the ideal weight vector is the one that points exactly opposite from that training instance. Now this boundary is going to be the farthest possible from the from that data instance, while also ensuring that it's being classified as the negative class. And now, if I'm given a collection of data points, this is the simple rule, just these two, right? Are these rules making sense to both of you guys? To all of you guys, there's nothing magical over here. It's very simple intuition, right? And so I'm going to build on this. This is the famous perceptron learning algorithm. You're given a collection of training data points where every data instance has a label either +1 or -1, and I'm trying to learn the hyperplane. So it's an iterative algorithm. I'm going to start off with some arbitrary W. Then I classify all my data points. Anytime I find a data instance that is misclassified, I'm going to pull W towards the ideal vector, weight vector for that data instance. And again, I want to point out that the ideal weight vector for a negative instance is minus x, and ideal weight vector for a positive instance is plus x, right? So anytime I find a training data point that's misclassified, I'm going to try to pull the weight that represents the plane towards the ideal vector for the misclassified data point. So let's say these red and blue dots are my training data. I set up an initial vector W. That gave me the decision boundary shown by the line. If I go through all the data points, I find this blue dot, which is a positive class, is being misclassified as being negative, right? What is the ideal weight vector for this blue dot? It's something that points directly at the blue dot, right? So I'm going to take this ideal weight vector, which is this arrow, and I'm going to add it to my actual weight. That gives me the updated weight shown by the new blue line. And that's going to give me a new decision boundary. That makes sense to everybody? Right? Very straightforward. Now I check all my data points again. I find this data point, which is the negative class, which is misclassified. What is the ideal weight vector for this guy? Exactly opposite it, right? So that is the weight vector here. That is the vector. The ideal weight vector for that is exactly opposite it. And so I'm going to add that to my current weight. Basically, I'm dragging the weight towards the ideal weight vector for my misclassified instance. It gives me a new weight and a new boundary, and now nothing is misclassified. I have a classifier. Very simple rule. And the math says that this simple procedure will always work provided the two classes are linearly separable. And it's not only going to just always work, the number of steps is finite. Meaning if the farthest data point is a distance r from the origin, and the best case boundary, the margin is gamma, then the number of steps is not going to be more than r over gamma squared. So basically it says that it's going to take, to cover a distance r, if the margin is gamma, the number of steps is polynomial in r over gamma, right? This is very nice. This is the perceptron algorithm. The problem is it doesn't work if the data are not linearly separable. Why? Because if the data are not linearly separable, you're always going to find errors. Then you're going to keep cycling and cycling and cycling. You will never stop. Now, that's for linearly separable problems. What about this guy? Are the classes linearly separable over here? They're not, right? So on the other hand, I'm sure we know that each of the perceptron is a linear classifier, and I can learn all of these linear classifiers so that the double pentagon is actually captured. So how can I learn this? We're going to see that it's impossible. Why? Let's continue to use the perceptron rule, right? Even if I'm using the perfect architecture, 5 neurons for the first perceptron, first pentagon, 5 for the second pentagon, then one guy combining those 5 lines for each of the 2 pentagons, a final OR. Can I use the perceptron learning rule for these guys? No. Why? Because here are all the boundaries that I wanted to learn. The first 5 neurons on the left are going to learn the 5 purple boundaries for the first pentagon. The 5 neurons on the right are going to learn the 5 black boundaries for the second pentagon. Observe that the training data are not linearly separable by any of these lines, right? So to simplify the problem, I'm going to give you this case where some oracle came by and gave me the weights of all the neurons except the one guy that's highlighted. If I learn that neuron properly, I have a perfect classifier. But the data I have are these guys, the red and blue. Can I learn that boundary from these data? Yes or no? Guys, come on. Yes? How can I learn that? Yeah, but these are not linearly separable. Are these data linearly separable? Yes, no, somebody says, okay, everybody say it aloud. Yes or no, one of the two, 1, 2, 3. Okay, thank you, right? So can I actually use the perceptron rule to learn this boundary? So what can I do? But we know that there is a perceptron that when modeled by that neuron is going to give you the first best double pentagon. What do I need to do to learn that boundary? Anybody? There's nothing you can do. What you really have to do is to relabel this data, right? I have to relabel the data so that I get two linearly separable classes, and then I can learn a boundary, and that boundary is going to contribute to the double pentagon, and then I get perfect classification. But can I use any odd relabeling, or is there one specific relabeling which is right? There's just one that is right? Everything else is going to give you something that's wrong. How do I find this one guy? Anyone? You have nothing that's classified right. The pattern is not complete, right? Okay, guys, you're all computer scientists, right? Or machine learning folks. You know the answer to this. So I'll wait. Yes. Any other solutions? Some guy at the back, someone at the back, do you want to give me an answer? What are the majority, right? So, but then this is what you have. Which ones do I relabel?
If we relabel the blue one, which is the minority on the upper side.
But I don't have the boundary. I'm learning the boundary. So the black line is not given to you. You're trying to learn the black line, right? You're trying to learn the black line for the highlighted neuron. And so it turns out the only way to do this is to try every possible way of relabeling the data. You try every possible way of relabeling the data, you relabel the data, then you try to learn this boundary. If the data are not linearly separable, you can't learn the boundary, it's going to loop. If the data are linearly separable, you learn a boundary, but then with that boundary, you're going to check the overall network to see if you got perfect classification. If you didn't, back to the drawing board. So how many different combinations do I have? I have n training instances. I have 2 raised to n possible relabelings. Each of them comes with a large computational load. So if I'm just learning that one perceptron so that the entire network is properly learned is computationally impossible. But the reality is that it's not just that one guy you have to learn. You have to learn all of these guys, right? So here is what you would have to do if you want to do this right. For every one of the perceptrons in your network, you're going to try every possible way of relabeling the data. Learn the boundary, then see if this combination gives you perfect classification. If it doesn't, go back, change things. So the number of possibilities you have to attempt is exponential or super exponential. This does not work. This is theoretically what you'd want to do, but this will not work, right? Because it's infeasible. And so, because if you get the one relabeling wrong for one neuron, the entire thing is going to collapse, right? And so you must know the desired output of every neuron for every training instance in order to learn the neuron. So, which means the outputs for every neuron should be such that they are you have two linearly separable classes, and all these linear separators must somehow combine to give you the correct decision boundary. It's a very complex problem. It is infeasible. And this is where things were right after Frank Rosenblatt introduced the multi-layer perceptron, right? So training this network using the perceptron rule is a combinatorial optimization problem. You don't know the outputs of the individual intermediate neurons for any training output, which means that you're not just training the network, you're also discovering what is the correct output for each neuron. And this you're doing through a search process, exhaustive search, and that's the only way to make the whole thing work. So this is exponential in time complexity. It's not a feasible solution. And when people realize this, work on neural networks stopped for a very long time, because how do you get around this problem? Widrow and Hopf came up with a with a greedy approximation, the famous Widrow delta rule. And it kind of works, but it didn't go all the way there. And many, many years later, when we spoke to Bernie Widrow, he said, oops, I missed back propagation because he was so close. Now, what was the trick? The trick has to do with this, that the manner in which we are computing correct and wrong doesn't work. So let's say I have these two classes of data, blue data and red data, one-dimensional inputs. The label is either 0 or 1, right? So 0 is the line in the middle, 1 is the line on top. So the perfect classifier is the one shown by the green line. All the red dots are labeled as 1, all the blue dots are labeled as 0. But then suppose I have a current setting of the perceptron, which gives me the dotted line. That dotted line is misclassifying two instances, right? Now the only parameter I've got is the threshold at which it goes from 0 to 1. If I've changed the threshold by a small amount and shift it right, will the error change? No, right? If I shift it left, will it change a little bit? So does a small shift tell me if I'm going in the correct direction or the wrong direction? It does not, right? So the problem really here is that if I start off with a wrong classifier, the only way I have of improving the classifier is to perturb my parameters and see if this changes the overall error. But a small perturbation will not change anything, right? So in higher dimensions, it's the same thing. I got that blue line. That blue line is misclassifying some instances. I can swing it all the way to either of the red lines, and the number of errors will not change. So there's no way of getting an indication which way to go. And this is because the perceptron is a flat function with zero derivative everywhere except at 0, and at 0 it is non-differentiable, right? Which means you can vary the weights a whole lot without changing the error, and this will give you no indication of whether you're going in the correct direction or not. This means we have to change the manner in which we are doing things. And that's for a single perceptron. If you go to a more complex pattern like this, the individual neurons' weights can change a lot without changing the overall error, basically because the simple MLP is a large, flat, non-differentiable function. What I mean by non-differentiable is that the derivative is 0 everywhere, except at specific points where the derivative is infinity. In any case, it gives me no indication of whether I'm doing things right or wrong. So we're going to change our way of computing the mismatch between what the network computes and what you want it to compute. And we're going to do it in such a way that modifying the classifier a little bit lets us know if you're going the right way or not. This requires changing two things. It requires changing your activation function number one, and number two, it requires changing the manner in which you evaluate the mismatch between the classifier output and the target output. And now we will no longer be counting errors, we'll be counting how much you're wrong by, right? So first thing, I'm going to get rid of the threshold activation, and I'm going to use some other activation function which is differentiable and gives me non-zero derivatives. And so this means that I will be able to tell you how much a small perturbation of the input perturbs the output. One. Second, I'm going to change the manner in which I count the error. Now in the upper figure, I showed you what we get when I simply count the number of errors. If I change the threshold from T1 to T2, the number of errors didn't change. So it doesn't tell me whether going from T1 to T2 is good or bad. Instead of using that Heaviside function, I'm going to use a smoother function like the blue one at the bottom. And now, instead of simply counting errors, I can still use this blue line for classification. I can say the output is class 1 whenever the value is greater than 0.5, and it's class 0 whenever the value is less than 0.5. But instead of counting errors, I'm actually going to count the total distance of the training data points from the curve. And so you can see that on the figure to the left, the total distance length of the two red lines is greater than in the figure to the right. And the difference between the two figures is that the curve has moved leftwards. And so that is telling me that moving the curve leftwards is a good thing to do. And so now it tells me which way to change my parameters. But is this the real error function that I'm trying to optimize, this total distance? Yes or no? Yes or no? Okay, why not? That's right? So the risk over here is that if I'm using this distance, then I can change the training data distribution to give you an entirely wrong answer. Can you think of an example of how? Can anybody think of an example of how this mechanism can give you a completely wrong answer and push this boundary, for instance, from here all the way out here? How would that happen? Anyone? No outliers. I'm giving you perfect data, right? Perfectly classifiable data. How would that happen? Anyone? Perfect, right? So if I have like 1,000,000,000,000 red data points out here, because that curve never actually goes to 1, at those 1,000,000,000 data points, the error is very small. But cumulatively, those 1,000,000,000 data points are going to give you a very large number. And so they're going to keep pushing the curve leftwards so that the cumulative error is reduced to 0. And so simply by piling more and more and more correct data out here, I can push the curve out to the far left where it's completely useless. That makes sense to everybody? Right? And so you can see that this proxy that we are using to train our models is not perfect. It's actually very sensitive to imbalances in data and data laid the wrong way, even though they're not actually telling lies. These are honest data, but they can make you do wrong things. Okay? So once we have this, then it's easy enough for us to see how this can be used to optimize the model properly, because it tells you whether small perturbations are improving or reducing the error. But then it comes with this additional risk is that if the data are not properly distributed, it can make you go to a completely wrong answer and be entirely happy with it, right? Okay, that makes sense to everybody? Okay. Now, the other issue is that we don't actually get linearly separable data. So you're going to have red data on the blue side, blue data on the red side. The perceptron rule won't even work over here. What do we do here? So here's a two-dimensional example. You're trying to learn a Heaviside function from the dots, except that you've got red dots hanging in the air on the blue side. You've got blue dots lying on the floor on the red side. How do you learn a function? The perceptron rule doesn't work. So this is the one-dimensional example. Again, there is no, in one dimension, a linear classifier is a threshold. There is no unique threshold that will perfectly classify the red and the blue dots, right? So we have a problem. You can't just find the threshold. But then you have the other issue. A neural network is infinite, has infinite capacity. So I can keep increasing the number of neurons, increase the size of the network, and I can learn this boundary. Is this a good boundary to learn? No, not really, right? It doesn't look like the right thing. Even if you're willing to accept that this is fine, I'm happy to live with this, then I can go one step further. And I say I have this issue where I have 100 data points, all of which have the same X, but the Ys are different for the two of them. In this case, what would you learn, right? What would be the correct output? So let's say I have 90 instances where the Y is 1 and 10 instances where the Y is 0. What should the output, even if you allow the network to do wild things, what should the output of the network be at this point? Should it be red? Should it be blue? Or should it be 0.9? What makes the most sense? 0.9, why? It's most informative, right? So out here. And so this guy makes sense. This makes sense if all of them are exactly the same value. But then if I perturb them a little bit and say they're all off by 10 raised to minus 17, which is the resolution of your floating point number, Now, should I suddenly allow things to go up and down wildly, or should I still be giving you 0.9? What do you think? Right? If things are slightly off, they're not all exactly the same x, would you still want 0.9 as the answer, or would you want things to go up and down, up and down, up and down within that 10 raised? You still want 0.9 to be an answer, right? So then the question is, how much am I allowing these things to spread by before I say this 0.9 is not a good answer? I don't want to answer that question. I'm going to change the problem setting. The way I will think about it is different. I'm going to say, again, in every case, the 0.9 over here is the posterior probability of one given x, right? Is a fraction of training data that had the value 1 for that x. So I'm going to say, I'm going to look at a small window around the current input. And I'm not plotting the value of any given input within the window. I'm going to plot for y the average output. So if all of the outputs were 0, the average is going to be 0. As I slide this window right, it's going to stay 0. At some point, I begin seeing some instances from the other class. At this point, the average has gone from 0 to slightly more than 0. As I keep going right, that average is going to keep going up. Eventually, I'm going to be seeing only ones, right? So this is the function I really want to model. And this is an approximation for the posterior probability of 1 given the input x. And so going back to our problem, the data are noisy. And when the data are noisy, you can't draw perfect boundaries. And so what you really want to do is to plot the posterior probability of the class 1 given the input. And that posterior probability curve typically has a curve of this kind, where it's 0 on one side and slides smoothly to 1 on the other side. And the logistic function is one of the functions, the sigmoid, which captures the small function. So this is what we actually use. The sigmoid with a single input models the a posteriori probability of class 1 given the input x. And this is where the whole thing comes from, that I'm using a sliding window, right? But then you never really computed probabilities. If you've been training neural networks, you threw in some KL cross entropy loss. You trained your classifier. Where did you learn posterior probabilities? Where did the probability model come in? It was always there. And why do I claim this, right? Before this, again, a sigmoid perceptron with a single input models a posteriori probability of the class 1 given the input. In the two-dimensional case, it's the same thing. You're going to have blue dots on the floor on the red side, red dots in the sky on the blue side. But the actual function you're going to learn is still a sigmoid. And the sigmoid is this sheet which goes like this. And it's still a linear classifier. The function is nonlinear, but it's a linear classifier because when I want to perform actual classification, I'm going to say, what is the place where this value of this function crosses from being below 0.5 to above 0.5. And that locus tends to be a hyperplane. It's straight. So although the function is nonlinear, it's a linear classifier, right? But again, this is what we're going to try to learn, the posterior probability of the class 1 given the input. And that has this form, right? It's 1 over 1 plus e raised to the standard sigmoid function. Now, going back into how this relates to how you actually train networks. Let's look at the math, right? So this is P of 1 given the input. It's 1 over 1 plus e raised to minus of W0 plus W1x. So what is the probability of minus 1? It's 1 minus P of 1, which is going to give you 1 over 1 plus e raised to plus W0 plus W1x. So I can write these two as a combined formula. And I can say the probability of any y given x, where y can be either plus 1 or minus 1, is the 1 over 1 plus e raised to minus of y times W0 plus W1x. So you can compare it to the two formulae on the top. You can see that it's correct for y equals minus 1. It's correct for y equals 1. For y equals minus 1, it gives you this formula. For y equals plus 1, it gives you this formula. So this works, right? Everybody with me so far? Okay. Yes? Okay, thank you. And now, I know this is math. It puts me to sleep, but I'll show you. But then I'm given a bunch of training data, XY pairs. What is the joint probability of all of my training data, assuming they are IID, independent? It is the product over all terms, all training data, of the probability of the individual training instances, P of xy, which in turn, I can write this as P of x times P of y given x, and P of y given x is the formula that we just saw. And so I've just written this joint probability of my entire training data in terms of the formula that I have from my model for the posterior probability of y given x, right? How many of you have heard of the term maximum likelihood training? Many of you have, right? If you've done any machine learning, what do we do in maximum likelihood training? We learn the parameters of the model to maximize the probability of the training data. So I'm going to do the same thing over here. I'm going to write down the probability of my training data, as we just saw, or better, the log probability, because it converts sums to products to sums, which is the sum overall training data of log of P of x minus sum overall training data of the log of the sigmoid, the softmax, computed at the training data. This first term doesn't depend on the network parameters, so I can ignore it. The second term is the only term that I have to worry about, and I want to maximize it. So I'm maximizing minus of something, which is the same as minimizing that term, right? So I can either learn the model parameters to maximize the log of the probability of the training data, or alternately minimize the log of the denominator of the sigmoid. And for those of you who have actually been working on neural networks, the second term that you'll realize that this is exactly the cross entropy loss that you minimize when you train neural networks. So it turns out that when you actually train neural networks to minimize cross entropy loss, what you're really doing is maximizing the a posteriori probability of the class given the data, which in turn is the same as maximizing the probability of the training data itself. It has to be done using gradient descent. But the magic nobody told you about is that your neural network is actually computing, for a single perceptron at least, your neural network is actually computing the posterior probability of classes given the training data, and your training is actually a statistical mechanism to learn how to compute these posterior probabilities properly. That's for a single perceptron. Okay? But then let's go back to the more complex problem, the nonlinear classifiers. And here, first, instead of looking at a crazy situation where you have blue dots on the red side and the red dots on the blue side, I'm going to look at the cleaner situation where the red and blue are cleanly separable, right? If the red and blue are cleanly separable, here is a model that we know can perfectly learn to classify these two pentagons, right? But for this model to work, the final output guy, that's just a perceptron. And that perceptron is a linear classifier, right? So if the perceptron is a linear classifier, for it to be able to do a perfect job of separating the red dots from the blue dots, by the time the red and the blue dots come to this final perceptron, they should be perfectly linearly separable. So although the data start off looking like the double pentagon out there, after the data have gone through the rest of the network, when they come to the final neuron, which works on two inputs, in that y1, y2 space, the data have to be linearly separable. Otherwise, you're not going to be able to do a perfect job of classification. That makes sense? Right? And so that means the network actually has two components. It has, firstly, this box, which moves all your data around. The data that started off like this, that box is going to begin moving all of the individual data instances until they are linearly separable. And then the final output layer is actually doing a job of separating these two guys. And so the network can be thought of as a linear classifier at the output And the rest of the network is a transformation that transforms data from these nonlinear classes into this new space where they're organized to be linearly separable. And so, it actually leads to some interesting solutions. I can train a neural network. If I train the neural network, I know that by the time I get to the classification layer, the data are linearly separable. I can use those representations as features to train some other linear classifier, which may be better, right? Like an SVM. And this is true for any sufficient structure. It doesn't have to be just the optimal structure. If the structure is capable of learning to classify the data properly, and if it does do so, it means that the network all the way to the final layer is basically a transformation that moves the data around so that they are linearly separable. And then the final layer is actually doing a job, the separation job. Okay. So mathematically, again, I have the y. The data are almost, or they're either perfectly or almost perfectly linearly separable in the space of y. And the network until the second to last layer is just a nonlinear function that converts the input space of x into the feature space y, where the classes are maximally linearly separable. Now, I was looking at the case where the red and the blue were cleanly separated, but that usually doesn't happen in real life. You're going to have noisy data, red data on the blue side, blue data on the red side. So what happens here? Same thing. The feature extraction layer, that's what I call everything until the final layer, is basically a transformation that transforms the data such that the posterior probability of the classes can be modeled by a logistic or a softmax. And the output logistic computes the posterior probability of the classes. So the overall model just remains a statistical model that actually computes, it learns to compute the posterior probabilities of classes given the data X. So you're not really thinking in terms of statistics when you train your neural network. You're just throwing it in, you're doing a forward pass, you're computing the outputs, then you're computing a cross entropy loss, you're training the network to minimize the cross entropy loss. And maybe you're not thinking too hard about what it's actually learning. But what it is actually learning is a statistical model that learns to estimate the posterior probabilities of the classes given X. It's not an approximation, it's not a hack. It is an exact statement within the constraints that the model itself imposes. That's a pretty magical thing. So the story so far, a classification MLP actually comprises two components. There's a feature extraction network that converts the inputs into linearly separable features or nearly linearly separable features, and a final linear classifier that operates on these linearly separable features. And training the MLP is actually a statistical exercise. It finds the parameters that maximize the conditional probability of the label given the input, right? Questions? I'm going to switch gears. So yes, no. Okay, thank you. Easier that way. Next time I'll expect a louder no, right? So what do the lower layer, so we've seen what happens at the outer layer. We've seen what the entire network does. What does the rest of the network do, right? They do compute features, but how do they look? So there are several hypotheses that people came up with for how the model actually learns to move data around so that they are linearly separable, so that the final neuron can actually do its job, the output layer can do its job. And here is a very nice visualization of how this happens. Pay attention over here, those of you who are asleep, because you have moving objects on the screen, and we all know that moving objects on the screen wake people up. So I'm going to try to model a circular decision boundary. It doesn't look like a circle, that's because the figure is distorted, but this guy here, okay? And this is a one hidden layer neuron network with 3 neurons in the hidden layer. they have tan-H activation, and the idea is to learn the network so that it learns the circular boundary. We have 1,000 training data points. Now let me first do the animation, then I'll explain what happens. The input is two-dimensional, right? The hidden layer is 3 dimensions. So what is the first thing that happens? I'm multiplying my input by a 3 cross 2 weight matrix, and it ends up in 3 dimensions, right? If I take a two-dimensional surface and multiply it by a 3 cross 2 matrix, what do I get? Do I get a 3-dimensional volume? What do I get? Or will I get something, will I get a 2-dimensional surface in 3 dimensions? What will I get? Somebody. If I take two-dimensional, if I take a 2D space and multiply it by a 3 cross 2 matrix, what does it say? Yeah. It's going to be a 2-dimensional surface in 3 dimensions because you're not filling out the 3rd dimension, right? So what will happen is that the first layer of the network, which is the weight multiplication, is going to take this 2-dimensional surface, it's going to put it somewhere at some orientation in the 3D space, right? But it's still going to be a flat surface. Then I apply a tan-H activation to it. What will happen to this surface? Is it going to remain planar or is it going to bend? It's going to bend, right? The activation, the weight multiplication by the weight matrix puts it in this 3D space. The tan-H activation is going to bend this surface to look curved. And then I multiply that by a 1 cross 3 weight vector. What happens then? If I multiply by a 1 cross 3 weight vector, what happens? So I have this curved surface. Let's say it's this cup. I multiply it by a 1 cross 3 vector. What happens? It's going, no, the output is one-dimensional. It's going to collapse this whole thing. It's going to project it down onto a one-dimensional line, correct? So those are the 3 operations that happen. First, I take this 2-dimensional surface, I put it in 3D space, then I bend it, then I project it onto a 1D line. Let's see what happens over here as we train. So you can see with the figure to the left that it's searching through all possible ways of orienting this surface until it finds one. And then at each orientation, it's warping the surface using the tan-H activation, and then finally projecting it down onto a single line where it's also trying to find the orientation of the line. And so the overall sequence of operations is that it's trying to find how to orient this plane in 3 dimensions so that when it's twisted and then I project it down to one line, the red and the blue dots get separated. And now I can apply a threshold and I'm separating the red and the blue dots. So, you can actually see how the network operates. It's pretty interesting. Is this figure making sense to you guys, to all of you guys? Right. So this is basically what's happening when the model is learning. It's learning to sort of move all of your data around and bend it so that in the end, all the classes become linearly separable. But then this is a very simple toy example. Let's look at a more realistic example over here. This is CIFAR 10, where we were modeling this using a 11-layer network, 11 hidden layer network. And each of the colors is a different class, right? What happens when I train this network? You can see how, as the network is trained, the things get segregated. And each of the classes becomes this convex region, which is linearly separated from the other classes. And the linear separability between the classes keeps increasing as you go through the network. Here's the animation is a bit too fast, but here it is again, right? You can see how the whole thing changes. Let me show this in 3 dimensions. It's easier to see. And so you can see what is happening. As you go through the network, the classes become increasingly linearly separable until finally at the output layer, they're all far apart. And now you can use a linear classifier to separate the classes. Two observations over here. There are 11 layers. Where do the classes first become linearly separable in this example? Anyone? Where do they first become? Can you speak up, please? They're linearly separable already by layer 7. Okay, so that one over there. And then afterwards, what happened? The separation between the classes keeps increasing, right? So typically when you train these networks, what happens is that once they are trained, the classes actually become linearly separable fairly early. And then the final few layers are just moving these classes further and further apart, which is why when you train a nice deep network with 150 layers, after you're done training, you can throw away the final 50 layers and just learn a linear classifier on the reduced representation, and you'll still be able to do a job that's just fine, because the final layers of the network focus on just pushing the classes further apart. But then again, you can see what is happening over here, that as the data go through the network, they become increasingly linearly separable. So far so good. That's a high level idea of what's going on, right? But then let's look further inside. We've seen what happens at the output. We've seen what happens through the network. But then let's look at the individual neurons themselves. Again, what does the individual neuron look like? The individual neuron is a perceptron. It's computing the inner product between a weight vector and its input. And if I use a threshold activation, which is good for intuition again, if the inner product exceeds a threshold, the perceptron fires, otherwise it doesn't fire. Again, geometrically, what this means is this. The weight vector represents a template. It's the pattern that the model is looking for. And it's looking at a small cone around this template. And if the input falls within this cone, the neuron is going to fire. Otherwise, it doesn't fire, right? And so basically, the perceptron fires if the input is within a specified angle of the weight, which represents a convex region on the surface of the sphere. You can think of the network as a Boolean function over these regions. The overall decision region, however, can be arbitrarily complex. So the bottom line is that the neuron fires if the input vector is close enough to the weight vector. That is, if the input pattern matches the weight pattern closely enough. Which is why we said that I can use this intuition to actually handcraft perceptrons in networks, right? If I want to recognize the digit 2 on my LED grid, I'm trying to figure out if the input looks like 2. So the weights must look like 2, right? And then if the inputs fall within some small angle of 2, it's going to fire. Otherwise, it's not going to fire. So the perceptron is actually a correlation filter. And then if I want to build something more complex, like looking at these examples and saying if this is a digit or not, I can, of course, handcraft it. But if I, instead of handcrafting, if I actually train the network, I expect the behavior to be much the same. I expect the first layer perceptrons to learn to detect specific features in the input, like horizontal lines, diagonal lines, localized regions. And I can tell you which patterns each perceptron is detecting simply by inspecting the weights. If the weights are 0 everywhere except in this small vertical region, it means that perceptron is detecting if a vertical line happens in that region. If the weights just have a small horizontal line, it means that the perceptron is learning to detect if a small horizontal line occurs in the input. The second layer neurons, of course, combine these guys to form more complex patterns, and then you can take a final decision. Yes?
Will those neurons also have a similar functionality? Like
You're going to end up with a lot of duplication.
a lot of duplication, and we could use like different paths to get the same.
Pretty much, yeah. You can end up learning sub-patterns, but more often than not, you'll also end up with lots of duplications, right? But that's not the key bit. The key bit is this. So let's say I've trained this network. Okay. And then I'm going to do something very interesting. I'm going to start off by starting off with a empty slate, empty figure. And then I pass some input through the network. And then I inspect each one of these first layer neurons. And so let's say this neuron has fired. Then I know that there's a horizontal line in the middle, right? So in my empty slot, I just go and fill the horizontal line because this was what the first neuron found. Then I scan through these guys, and then I find that this neuron also fired. And this neuron is looking for a horizontal line at the bottom. So then I go in and fill in the horizontal line at the bottom in my empty slot. And then I continue scanning. Maybe I find the guy at the extreme left is fired. So there's a horizontal line at the bottom, at the top. So simply by inspecting the outputs of my first layer neurons and then filling in the weight patterns for the neurons that did fire, I can reconstruct something from the input, right? How much would I reconstruct if I did this? Mathematically, this is the operation. If I'm filling in the weights, I'm basically multiplying these outputs by the transpose of the weight vector, right? Would the output look like the input if I did this? I'm just detecting each pattern, and if the pattern occurs, I'm filling it in. What would it look like? Anybody? Guys, you're sleeping, so you're going to see mostly the same digit. Not exactly, because things that don't contribute to classification will not show up, but everything that's significant will show up, right? So is this making sense to everybody? Okay. I can make this more explicit. Instead of saying, in this network, it's going to lose a few things. Any features that are not important for digit classification will not show up, right? So, this is only retaining distinctly digit-like or obviously not digit-like features. The rest are irrelevant, they will be lost. But then I can make it explicit. I can say, make the output like the input itself, in which case I would be minimizing the error between the output and the input. This is what we all call an autoencoder. An encoder learns to detect all the most significant patterns in the signal in the input. The decoder is recombining these guys to reconstruct the input, right? Now, this is the basis of everything. The reason I'm going over this is the basis of pretty much all generative models that people use these days: AEs, VAEs, diffusion models, flows. If you're interested in some deep, headache-inspiring mathematics, just let me know. I'll give you 60 pages of math, but I'm going to compress it into like 10 slides. Okay. So what is the simplest autoencoder? The simplest autoencoder is something very simple. It has only one hidden neuron, and I'm trying to reconstruct the output. And to make it really simple, I'm going to say that hidden neuron just has an identity activation. Whatever comes in goes out, right? So the input is Wx, that goes out, so it becomes W transpose Wx, right? Now, if I train this to minimize the error between the output and the input, here's what you get. X is the input, W transpose Wx is the reconstructed output. I'm minimizing the error between the two. This formula, where I'm basically projecting it on to a single line, that's just PCA, right? This is principal component analysis. So what this autoencoder with a single hidden neuron and linear activation is doing is performing PCA. And importantly, if you look at the second half, the output always looks like W transpose something, meaning it's basically scaling the weight vector W differently for each input. So which means that the autoencoder finds the direction of maximum energy or maximum variance, regardless of what input X you give it. The intermediate value is Wx, which is a scalar. And that scalar is multiplying W transpose to give you the reconstruction, which means the output is always going to be some scaling of the vector W. And so the vector W is going to give you the principal component direction. And the lower part of the network is basically finding the position of each input on this principal component. This making sense to everybody? Right? It's just PCA. This is with one component. Now, the key thing is this. It doesn't matter what the input is. Once this model is learned, the output is always going to be some scaling of W. It cannot reconstruct two-dimensional data. It's only going to reconstruct extensions of the vector W, shown in the blue line, right? Same thing, if I have 2 dimensions, then it's going to find a principal subspace. If I have, say, an n-dimensional input and a two-dimensional hidden representation, and if I have linear activations, I'm still speaking of linear activations, the math is the same. It's going to find you the principal two-dimensional subspace. If the hidden layer has k dimensions, it's going to find a k-dimensional principal subspace. It's always linear. And the interesting thing is, regardless of, once the model is learned, regardless of what input I provided, the output is always going to be on this principal subspace. So where is all of this taking us? First, some terminology. Encoder and decoder, it's an autoencoder. The autoencoder is the analysis net, which computes a hidden representation, which basically says where on this principal subspace I am. And the decoder is the synthesis network, which recomposes the data from the hidden representation. You're all familiar with this. But then going back to what our data are, if the hidden activation is linear, then the principal subspace is always going to be a plane. And so it's performing planar principal component analysis. But if the decoder has nonlinear activations, we just saw what nonlinear activations do. It folds the surface, right? And so now this model ends up learning, instead of learning a plane, a linear plane, hyperplane, to best represent the data, it ends up learning a curved surface. So it learns a manifold, a nonlinear manifold. And so anytime you have nonlinear activations in the decoder of an autoencoder, what you're really doing is finding the curved surface such that if you project all the data onto this curved surface, the error is minimized. And so this is nonlinear principal component analysis, or also called principal manifold analysis. Now, what is a principal manifold? It turns out that in the machine learning literature, there's a lot of controversy on even defining principal manifolds. There are 2 different definitions, but it just so happens that whatever you learn using these autoencoders satisfies both definitions. You actually learn the principal curved surface that best captures the structure of the distribution of the data. And so the autoencoder with nonlinearity, it performs nonlinear principal component analysis or principal manifold analysis. And deeper networks in the decoder can capture more complicated manifolds. The encoder can be simple. It's all in the complexity of the decoder, right? These are the deep autoencoders. So here are some examples. In this case, I have data, 2-dimensional data scattered approximately on a spiral, right? So I've learned an autoencoder where eventually the hidden representation is only 1 dimension. And then the decoder goes back from 1 dimension to 2 dimensions. The architecture of the network is given over here. It's it's an MLP with 5 residual blocks, each with 64 hidden units. That's besides the point. The point is this. Look at what the decoder actually captures. The decoder is putting the entire data on a learned spiral, right? Of course, it's not a perfectly learned spiral. You can see a line that hops across 2 legs, and there's some portion which does some wiggly stuff at the end. What do you think is happening at those 2 places where it's hopping between legs and doing some crazy wiggles? What's happening there? Anyone? Those are regions where there was no training data. So where there's no training data, it can do crazy stuff. But everywhere that there was training data, it learned the exact spiral that the data lay on, right? Which means that the decoder can only reconstruct data on the spiral, nowhere else. Or here's another example. This was something that looks like a sinusoid. Once again, we've learned an autoencoder which brings things down to one dimension and then constructs it. So the decoder can only now construct a one-dimensional curve and two-dimensional space. And the specific curve it's learned to construct is the sinusoid in two-dimensional space. And you can see that it's actually learning the principal structure, the principal manifold of the data, right? And so you put this to use. So when the hidden representation of the lower is a lower dimensionality than the input, we call this a bottleneck. And in this case, what the model is doing, this is the bottom line, is performing nonlinear principal component analysis or principal manifold analysis. It learns the manifold of the data if properly trained. And now this is the interesting bit. Because you've learned the manifold of the data, the decoder over here, the portion of the network, the upper portion of the network, it can only generate data on this manifold. So over here, for example, it doesn't matter what z value I give the decoder, what input I give the decoder. The output will always be on this spiral. It's not going to be anywhere else. So it has learned the principal structure of the data. So for example, if I learned an autoencoder on digits, and then I threw away the encoder, and I fed any odd value to the decoder portion of this network, what it's going to come up with is something that looks like a digit. Simply because the decoder has learned only the manifold of digits, everything that it can generate is on this digit manifold. It's not going to be all digits, but it's going to look like a digit, right? Or here is this example where we trained an autoencoder on a clarinet. Then you throw away the encoder, and then on the decoder, you just feed it some random values. And here's what it produces. It ends up producing something that sounds like a clarinet. Different inputs, different random inputs at Z, right? It only sounds like a clarinet because it's learned this data manifold. It's learned the manifold for clarinets. Here is another one. This is for a saxophone. This is a clarinet, right? Here. I've not given it anything. I've not told it not to produce noise. There are no instructions. All I've done is train this decoder on autoencoder on saxophone examples in the first case, clarinet examples in the second case. I throw away the encoder. I feed the decoder random inputs, and out comes something that sounds like a saxophone. It's not a pure note, but it's some combination of sax notes. It's some combination of clarinet notes, right? It learns to produce the appropriate thing. And I'm going to finish kind of early because I know you guys are sleepy, but still. Here's a cute little application for this. I'm going to do sound separation. We did this many years ago, but this is literally about 10 lines of MATLAB code, which means about 25 lines of Python because you need all the rest of the gunk at the top and the bottom. This is what we call dictionary-based representation. The basic idea is to, now in sound sources, let's say I'm trying to separate musical instruments, right? If I'm trying to separate musical instruments, I've got somebody playing the violin, I've got somebody playing the saxophone. Then if I know what are all the things that a violin can produce, a violin can produce violin notes. A saxophone can produce saxophone notes. So if somebody gives me a recording which includes both violin and saxophone, what I really have to do is to say what is the combination of violin notes and the combination of saxophone notes, which, if I played them all together, sounds exactly like what I just heard. Then I can go back and separate, the violin portion and the saxophone portion, right? It's a very simple idea. This is what a dictionary-based method does. And so the basic idea, you want to learn a dictionary of building blocks for each sound source. And all signals from that source are basically composed of entries from the dictionary. So if you want to separate, say, guitar from drums, you're going to learn a guitar dictionary from some training data. And you're going to learn some drum dictionary from some training data of drums. And now when you get a mixed recording, you're going to figure out what entries from the guitar dictionary and what entries from the drum dictionary must be combined to produce this recording you just heard. And once you figure that out, then you can separate out the guitar components from the drum components. So we're going to do this using what we just learned, right? So separation, you just identify the components, the combination of entries from both dictionaries that compose the mixed signal. And the composition from the identified dictionary entries gives you the separated signals, right? I'm going to do this using what we just learned about autoencoders. Now, in an autoencoder, I just showed you, if I learn an autoencoder from a specific class of data, like saxophone music, then the decoder and the autoencoder can only generate data on that manifold. So regardless of how I excite it, the output is going to be something saxophony, right? So also when I train it on oboes, regardless, once I train the autoencoder, if I throw away the encoder, the decoder can only generate things that sound somewhat oboe, right? So let's put that to action. What happened here? Come on. So in my example, I'm going to learn two autoencoders. I'm trying to separate two sounds, a mixture of two classes of sounds. I'm going to learn one autoencoder for the first category, say guitars. I'm going to train a second autoencoder for the second category, which are, say, drums. I throw away both the encoders, so I'm left with only the decoders. And now when I get a mixed recording, I only have to find out what input to give the guitar decoder and what input to give the drum decoder so that their outputs, when summed, sounds like my mixed recording. And this I can do using back propagation. I have an output, I can propagate errors all the way back, and I can actually learn the inputs to both these decoders so that their outputs, when combined, sound like my target sound. And thereafter, just the individual output of the outputs of the two decoders is going to give me the separated sounds, right? Let's see if this works. Come on. I need more space here. Instruments, right? So nothing very fancy, right? And these are actually two very tiny neural networks that we trained, autoencoders, one trained for the violin, the other trained for the, I think it's oboe or saxophone. And then you use their decoders to do the separation. That does a pretty good job. Again, the point we are trying to make is that what these models learn, they're learning structures, they're learning features. We looked at these networks from various perspectives. What is a network? What does it learn? How does it model stuff? How does it learn to separate stuff? What does each component actually capture? And the final bit we saw that was that when done properly, they actually capture the structure of the data, which you could put to use for generative purposes, which is, here's an example, right? I will stop right here with this, which gives you guys, classification networks learn to predict a posteriori probabilities of classes. And neural networks can be also used. Again, this is a very mechanistic view of life. They can be used to perform nonlinear or linear PCA, but that's not the point. The point is what they actually learn. And we spent 3 hours, the better part of 3 hours going through that. I hope it was instructive. I'll stop right here and let you guys out. Any questions? Yeah. Someone had a question? Okay, no question. Okay, there's one question up front, yes. And then the guy, he's holding you up.
I apologize. So what are the limitations of these vanilla autoencoders? Because I know that as time progressed, different ones like variational autoencoders also emerged. So do autoencoders, the ones that you explained in the lecture, have some limitations or?
Yeah, of course, right. So something that I didn't go over, which is look at what happens outside the training data limits. We have no control, right? So when I just train an autoencoder over here, I didn't tell you what range of Z's were valid. It can learn Z from -7 to -12, -infinity to +infinity, 3 to 8. You have no control over the exact Z's that you learn, range of Z's, because the model is just learned on block. And so as a result, if I want to use this for generative purposes, I really don't know how to excite this model. And so what VAEs do is to actually impose restrictions on the Z so that the whole behavior is much more predictable. Without it, the behavior is not predictable. The extensions from there is that you're basically transforming the distribution of Z's to the distribution of X's. It's a big jump. If you stage it, you end up with things like diffusion models and flow models, but they're all just, it's a linear progression of this basic idea with control on Z.
Thank you.
All right, we're all out of questions. Thank you all.